Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, large ideas move gently, and tonight the universe will take its time. This evening, we're looking upward toward one of the grandest events space can offer. What really happens when two galaxies collide? It sounds dramatic, doesn't it? Like a headline written by the cosmos itself. You might picture stars smashing together, worlds thrown like pebbles, fire in every direction, and the sort of chaos that would make even the most confident astronomer quietly sit down. And yet, as with so many things in science, the truth is both calmer and stranger. A galaxy is not a solid object. It is not a plate, or a stone, or a crowded city block barreling through the dark. It is more like an enormous arrangement of distance, gravity, dust, gas, light, and patience. Billions of stars held in a slow relationship with one another, spread across spaces so vast that our everyday language struggles to describe them without becoming slightly dizzy. So when two galaxies meet, they do not simply crash in the way cars crash, or waves crash, or cymbals crash, in an over-enthusiastic orchestra. They drift into one another across millions of years. They tug, they stretch, they reshape, they exchange material, they stir sleeping clouds of gas into new generations of stars. They bend each other's structure until both become something neither once was. In short, they collide the way only the universe can collide. Slowly enough that if you watched it happen with your own eyes, you might wonder whether anything was changing at all. Before we begin our quiet journey through these wandering star cities, I'd love to know where you're listening from tonight. What part of the world is holding you right now? And what time is it in your little corner of Earth? Perhaps it is late evening. Perhaps dawn is beginning somewhere outside your window. Perhaps you're wrapped in blankets, pretending not to check tomorrow's responsibilities for at least a little while longer. If you find this voyage soothing, interesting, or simply a pleasant place to rest your thoughts, I'd be grateful if you gave the video a like and maybe subscribed. It helps this calm little observatory reach other listeners who may need a peaceful landing place at the end of their day. Now, get comfortable. Let your shoulders loosen. Let the room become less important for a while. We're about to think on scales so large that human schedules become charming little jokes. To understand two galaxies meeting, we should begin with a simpler question. What is a galaxy in the first place? When many people imagine one, they picture the familiar spiral shape seen in photographs. Bright arms curling outward from a glowing centre, like cream stirred into coffee. That image is beautiful, and in many cases accurate, but it is also incomplete. A galaxy is not just the visible swirl. It includes stars, certainly, but also immense clouds of hydrogen gas, lanes of dust, star clusters, wandering planets, dead stars, black holes, magnetic fields, and something even more mysterious, dark matter, the unseen mass whose gravity helps hold much of the structure together. Our own home, the Milky Way, is one such system. It contains hundreds of billions of stars, perhaps more. Among them is our modest sun, quietly doing its best to seem important from our local perspective. Yet in the scale of the galaxy, the sun is one resident among countless others, orbiting the centre once every roughly 230 million years. Since dinosaurs walked the Earth, our solar system has completed only about one full galactic lap, which is a humbling statistic if you enjoy feeling behind schedule. Galaxies come in different forms. Some are spirals, elegant and rotating. Some are ellipticals, more rounded and less structured, containing older stars and less gas. Some are irregular, shaped less like neat diagrams and more like the universe shrugging creatively. There are dwarf galaxies as well, smaller companions that orbit larger ones. The Milky Way itself has several. Space, it turns out, is not empty in the sense of lonely simplicity. It is full of systems, companions, streams, remnants, and ongoing relationships. And relationships lead us to collisions. For much of history, the night sky looked fixed. Stars seemed pinned in place, constellations held their shapes, the heavens appeared calm and permanent. Only with modern astronomy did we realise that everything is moving. The Earth spins, the Earth orbits the Sun orbits the Milky Way's centre, the Milky Way moves through space. Nearby galaxies move as well. Galaxy groups dance around shared centres of mass. Larger clusters drift and interact over immense spans of time. The universe is dynamic, restless, and in motion, but it moves with such patience that human senses mistake it for stillness. Imagine placing two icebergs in a dark ocean so vast that each takes ages to approach the other. Now replace the icebergs with collections of stars larger than language likes to manage. Remove the water, add gravity. Wait hundreds of millions of years. You're beginning to think in the right direction. When galaxies draw near, gravity is the first messenger. Long before visible overlap, each begins affecting the other. Stars feel tiny changes in their paths. Gas clouds shift. Outer regions distort. Dark matter halos, those enormous invisible envelopes surrounding galaxies, interpenetrate and tug. Nothing explodes at first. Nothing announces itself with trumpets. Instead, order begins to bend. This surprises many people because the word collision suggests impact. But galactic encounters are less like billiard balls and more like two swarms of fireflies, passing through one another while every firefly feels the pull of every other. Another surprise is this: stars almost never hit each other directly. That sounds impossible. If two galaxies each contain billions of stars and move through each other, surely stars must collide constantly. But stars are tiny compared with the distances between them. If our sun were the size of a grain of sand, the nearest star would still be many kilometres away. Galactic space inside galaxies is mostly emptiness, enormous emptiness, structured emptiness, gravitationally meaningful emptiness, but emptiness all the same. So when galaxies merge, stars usually pass by one another untouched, each continuing on a newly altered orbit. The systems collide. Individual stars mostly do not. This is one of the universe's favourite habits, making huge events out of almost nothing touching directly. Gas, however, is another matter. Unlike stars, clouds of gas can meet, compress, shock, and heat. When galactic gas clouds interact, they lose energy, bunch together, and can trigger waves of star formation. Regions that were once quiet begin producing hot young stars in large numbers. A merging galaxy may suddenly blaze with blue-white stellar nurseries, so a collision can be destructive in one sense, but creative in another. Old structures unravel, new stars are born, dust lanes twist. Central black holes may begin spiralling toward each other over time. Tidal tails, long streams of stars and gas, can stretch far into space like luminous ribbons flung from the encounter. Astronomers have photographed many such systems. Some look like cosmic roses, some resemble torn spirals, some appear mid-embrace, frozen in a stage of transformation that itself lasts longer than human civilization has existed. When we look at them, we're not seeing a rare accident. We're seeing a normal part of galaxy life. Galaxies grow by merging. Large galaxies often become large because they absorb smaller ones. Even the Milky Way bears evidence of past encounters. Streams of stars moving through our halo are leftovers of dwarf galaxies stretched apart and incorporated long ago. Our home has eaten before, it will likely do so again. And one future meeting is especially famous. The Andromeda Galaxy, our nearest large galactic neighbour, is moving toward us. Not in a dramatic tomorrow morning sense, so there is no need to cancel plans. But over billions of years, the Milky Way and Andromeda are expected to approach, interact, and eventually merge. The night sky of that distant era, if anyone is around to watch, would become extraordinary. Andromeda would grow larger over ages, then dominate the heavens, then distort into arcs and streams as both galaxies pass through one another repeatedly. but we're getting ahead of ourselves. Tonight we begin at the threshold, before the first close pass, before the tidal stretching, before new stars ignite in swarms, before central black holes draw near. Right now we're simply learning to replace the word crash with the word dance, because that is closer to reality. Not a graceful ballroom dance, perhaps, more a gravitational negotiation between two sprawling star nations, each arriving with billions of suns, invisible matter, ancient planets, and no intention of staying unchanged. It is also worth pausing to appreciate how absurdly slow these events are. A human life is too short to notice a galaxy turning. Entire civilizations rise and vanish in less time than it takes two neighbouring galaxies to significantly alter positions from our viewpoint. If you lived on a planet inside one of these systems, day-to-day life might continue for ages while the larger merger unfolded overhead so gradually that myths, calendars, religions, and empires could come and go beneath a changing but patient sky. That scale can feel alien at first, but it can also feel comforting. Not everything important happens quickly. Some transformations require distance, persistence, and time so generous that urgency has no place in it. Perhaps that is one reason the cosmos can be strangely calming. It reminds us that frantic pacing is not the only mode of existence. Somewhere far beyond our local concerns, galaxies are taking hundreds of millions of years to sort things out. Now consider something that seems backwards at first glance. One of the largest collisions in the universe is made possible by how little there is to hit. When we hear the word collision, our minds usually reach for familiar examples. Two cars meet at an intersection. Waves strike rocks. Shopping carts discover each other in a supermarket parking lot with great emotional intensity. In every case, collision means surfaces touching, material resisting material, energy released where solid things meet. That instinct serves us well on Earth. It does not serve us especially well in deep space. A galaxy appears dense in photographs because our eyes collect light from billions of stars compressed into a flat image. A spiral galaxy can look like a glowing pinwheel packed with brilliance from centre to edge. The picture suggests crowding. It suggests busy neighbourhoods where stars sit shoulder to shoulder, politely pretending not to notice one another. The reality is almost the opposite. Galaxies are mostly emptiness, not slightly empty, not some space between objects empty, vastly, extravagantly, almost comically empty. If you could travel through a typical region of the Milky Way, you would not weave through traffic. You would not dodge stars every few minutes. You would drift through enormous stretches of dark distance, where the nearest star might be trillions of kilometres away. This is why galactic encounters are so strange. Two immense systems can pass through one another, each containing hundreds of billions of stars, and yet direct star-to-star impacts remain extraordinarily unlikely. Let's slow that idea down. Our Sun is about 1.39 million kilometres across. That sounds large because it is. You could fit more than 1 million Earths inside it by volume. But compared with the distance to the nearest star system, the Sun becomes tiny. The nearest stellar neighbour to the Sun is the Proxima Centauri, over 4 light-years away. A light-year is the distance light travels in 1 year, nearly 9.46 trillion kilometres. Even after saying the number, the mind tends to stare politely and decline to visualise it. So imagine shrinking the Sun to the size of a marble. On that scale, the nearest star would still be many hundreds of kilometres away, depending on how you scale the model. A marble in one city, another marble in a distant country, with mostly nothing in between. That is the typical style of stellar spacing. Stars are large objects separated by absurd distances. Because of this, if two galaxies merge, stars usually pass by one another with plenty of room to spare. Their paths bend due to gravity, but physical contact is rare enough that collision becomes almost misleading if we imagine smashing suns. What actually collides is structure. What actually interacts is gravity. What actually compresses is gas. And what actually transforms is the overall arrangement of everything, This is one of the universe's favourite lessons, scale changes meaning. A crowded city and a crowded galaxy are not crowded in the same sense. A galaxy can contain more stars than grains of sand on many beaches, yet still be mostly vacant volume. Even inside our own solar system, space is emptier than intuition expects. In textbook diagrams, planets look neatly spaced and visually close. Real scales would force diagrams so large they become useless on a page. If the Sun were a grapefruit, Earth might be a peppercorn many meters away. Neptune would be much farther still. And that is merely one star system. Now expand to galactic scale, where star systems themselves are separated by enormous gulfs. No wonder collisions become ghostly. Two galaxies can overlap visually, while most of their stars remain nowhere near one another. It is like two fog banks passing through each other, except each droplet is a star system, and gravity keeps changing every path. This emptiness also helps explain why the night sky is dark. If the universe were infinite, static, and evenly packed with stars, every line of sight would eventually end on a stellar surface. The sky would blaze. Instead, expansion, finite age, dust, and distribution matter greatly. Space is not a filled room. It is a place where distance dominates. Distance dominates almost everything in astronomy. That includes danger. People sometimes ask whether the future meeting between the Milky Way and the Andromeda Galaxy means stars will begin crashing around us. In general, no. The greater risk to a given planetary system would come from changing gravitational neighbourhoods, altered comet reservoirs, or rare close stellar passes over immense time, not suns striking each other like billiard balls. Even during a galactic merger, most star systems continue existing with tremendous personal space. That phrase, personal space, may be the most relatable way to describe a galaxy. Every star strongly prefers distance. Still, emptiness does not mean nothing matters. Gravity reaches across empty space beautifully well. It weakens with distance, yes, but it never entirely switches off. Every star, gas cloud, black hole, and dark matter halo contributes to the changing gravitational field of a galaxy. So while stars rarely hit, they constantly influence. Imagine standing in a vast hall with billions of people, each whispering instructions very softly. No single whisper from a distant stranger changes much, but together the crowd shapes where everyone drifts. That metaphor is imperfect, but it points in the right direction. Galactic collisions are collective events. The drama emerges not from one catastrophic impact, but from billions of tiny gravitational nudges integrated over time. This is why computer simulations of mergers are so useful. Astronomers model huge numbers of particles representing stars, gas, and dark matter, then let gravity evolve the system. Spirals distort, tails form, centers sink inward, new shapes emerge. Nothing dramatic needs to strike anything directly. The choreography comes from accumulated influence. Gas clouds, however, do behave differently from stars. Stars are compact and mostly pass through empty regions. Gas is spread out, diffuse, and able to collide with other gas. When two galaxies overlap, giant hydrogen clouds can ram together, shock, heat, cool, and collapse into dense knots. Those knots become nurseries for new stars. So while stars often miss, star-making material does not. This is one reason some merging galaxies shine with intense bursts of fresh blue stars. The emptiness that protects stars from collision does not protect gas from compression. Dust joins the story too. Tiny solid grains mixed with gas can obscure light, re-radiate energy in infrared wavelengths, and help cooling processes that assist cloud collapse. Merging systems can become dusty, bright, and turbulent in ways invisible light photographs only partly reveal. The famous antennae galaxies are a good example. Two galaxies in the process of merging, they display long tidal tails and vigorous star formation. Their beauty comes not from stars smashing together, but from gravity reshaping the systems and gas responding dramatically. The name antennae comes from those extended streams of material flung outward during the interaction. Again, not debris from a crash in the everyday sense, but stars and gas placed on new orbits by tidal forces. Emptiness makes these tails possible too. Because stars have room to move, a passing galaxy can stretch or sling vast populations outward without immediate recollision into dense walls of matter. The same emptiness that prevents impacts allows elegant large-scale distortions. There is also dark matter, the invisible majority component of many galaxies' mass. We do not see it directly, but we infer it from gravitational effects. Galaxies appear embedded in extended dark matter, halos much larger than their bright stellar disks. When galaxies approach, these halos interact first in a gravitational sense. Long before visible disks overlap, their unseen mass distributions begin altering motion. So in a real merger, one might say the invisible parts meet before the visible parts do. That is wonderfully strange. Two enormous unseen halos begin the conversation. Later, stars and gas reveal the consequences. Human intuition tends to rank visible things as the main event. The universe is less committed to that preference. If you could float between two approaching galaxies millions of years before their stars visually mingled, you might notice almost nothing by eye. Yet gravitationally the process would already be underway. This reminds us that emptiness is not absence. Empty space can contain fields, particles, radiation, motion, curvature, and potential. It can carry light for millions of years. It can host gravity's long reach. It can separate stars while allowing galaxies to bind. Even on smaller scales, vacuum is not nothing in the simple sense. Physics has spent the last century repeatedly informing us that nothing is more complicated than expected, and space seems pleased about it. Another odd result of emptiness is that galactic timescales become gentle. If galaxies were dense solids, mergers would be brief and violent. Because they are diffuse systems, interactions unfold over hundreds of millions or billions of years. A first close pass may distort both galaxies, then they swing apart, gravity slows them, they return. Another pass follows. Eventually, energy is redistributed, and the systems settle into one merged galaxy. This can take longer than multicellular life has existed on Earth. So when we say galaxies collide, we are compressing a patient epic into one sharp verb. Language does this often in astronomy. Stars are born over long cloud collapse phases. They die in events sometimes lasting eons before final transitions. Black holes consume matter through complex accretion processes. Galaxies collide while mostly missing each other. The verbs are helpful, but the reality is subtler. It may also be comforting. Some changes in life feel abrupt because they are close to us, on cosmic scales. Even major transformations often involve long periods of adjustment, repeated passes, gradual reshaping, and new structure emerging from disorder. The universe is not always in a rush. From Earth, our own lives occur in the midst of immense emptiness too. Between us and the nearest star lies vast, dark distance. Between galaxies, still greater gulfs. Yet from those gulfs comes starlight, gravitational influence, and eventually encounters that reshape whole systems. Distance separates, but it also defines relationship. Without space between stars, planetary orbits would be unstable and dangerous. Without room between galaxies, structure formation would look entirely different. Emptiness is not wasted volume. It is the condition that allows order to exist the way it does. That might be the deepest surprise in tonight's subject. A galactic collision becomes stranger than it sounds, because what seems empty is essential. What seems violent is mostly graceful, and what seems like impact is often orbit, drift, pull, and time. Take a moment now to imagine that all cities on Earth were lifted into the sky, stretched across impossible distances and replaced with stars. Roads would become streams of orbiting light. Neighborhoods would span thousands of light years. Downtown districts might hide black holes of extraordinary mass. Parks would be clouds of gas waiting to form new suns, and even then, the comparison would still be much too small. Before two galaxies can meet, it helps to know who is arriving. The word galaxy covers many kinds of structures. Some are elegant and rotating, some are rounder and older, some are messy in ways astronomers describe politely as irregular. Some are so massive and calm-looking that they seem less like cities of stars and more like ancient weather systems that forgot to move on. Each type carries its own history, and when galaxies interact, those histories matter. Let's begin with the most famous shape of all, the spiral galaxy. If you've ever seen a classic deep space image with graceful arms curling outward from a bright centre, chances are you were looking at a spiral. These galaxies are among the most photogenic residents of the cosmos, which is fortunate because they do seem to enjoy being photographed. A spiral galaxy typically has several main parts. At the centre sits a bulge, a rounded concentration of stars. Around that lies a flat rotating disk containing stars, gas and dust. Within the disk, spiral arms wind outward like lanes of brightness. Surrounding everything is a larger halo containing older stars, globular clusters and dark matter. Our own Milky Way is a barred spiral galaxy, meaning it has an elongated central bar of stars crossing the inner region, with spiral arms extending outward from the ends of that bar. This means humanity lives inside a rotating stellar disk with decorative architecture. The Milky Way is roughly 100,000 light-years across, perhaps more depending on how one measures faint outer structure. It contains hundreds of billions of stars, gas clouds, dust lanes, and a central supermassive black hole known as Sagittarius A star. Despite living inside it, we cannot step outside for a clean family portrait. We must infer its shape from internal maps, careful measurements, and the cosmic equivalent of trying to sketch a forest while standing among the trees. Spiral galaxies are often rich in gas and dust. That matters because gas is raw material for star formation. In spiral arms, density waves and cloud interactions can trigger the birth of young stars. These hot new stars glow blue-white, making the arms shine brightly. So when you see a spiral galaxy, you're often looking at a system where new generations are still arriving. There is motion, structure, rotation, and ongoing construction. Now contrast that with another major family, elliptical galaxies. Ellipticals are named for their rounded or stretched oval appearance. They range from nearly spherical to cigar-shaped. Unlike spirals, they usually lack obvious arms and prominent dust lanes. Their stars move in many directions rather than mostly circling in a flat disk. If spirals are busy rotating metropolises, ellipticals are more like vast old estates, where the traffic pattern became philosophical. Many elliptical galaxies contain older, redder stars and relatively little cold gas. That suggests lower rates of new star formation. They are often quieter in terms of stellar birth, though not always inactive in every sense. Some host energetic central black holes. Some contain hot gas halos glowing in X-rays. Quiet is relative in astronomy. Still, compared with gas-rich spirals, ellipticals often feel mature. They can also be enormous. Among the largest known galaxies and clusters are giant ellipticals, sometimes called CD galaxies, occupying central positions in galaxy clusters and surrounded by sprawling halos of stars. These systems likely grew through repeated mergers over long cosmic history, absorbing smaller galaxies the way a snowball gathers layers while rolling downhill for several billion years. One famous giant elliptical is Messier 87, often called M87. It hosts a supermassive black hole whose image became historically important when the Event Horizon Telescope captured the first direct image of a black hole shadow in 2019. So even galaxies that appear calm may hide remarkable engines at their centres. Then there are lenticular galaxies, sometimes labelled S0 galaxies. These are a sort of in-between category. They possess a disk like spirals, but little or no obvious spiral structure, and often reduced gas content. Imagine a spiral galaxy that tidied itself up, stopped making many new stars, and decided patterns were becoming unnecessary. Astronomy loves categories, but nature enjoys gradients. Many galaxies do not fit perfectly neat boxes. That brings us to irregular galaxies. Irregular galaxies lack the clean symmetry of spirals or ellipticals. Some are small dwarf systems shaped by internal chaos, low mass, or bursts of star formation. Others were once more orderly but became distorted by interactions. The Large Magellanic Cloud and Small Magellanic Cloud, visible from southern latitudes, are nearby examples of irregular dwarf galaxies interacting with each other and with the Milky Way. They are reminders that galaxies can be dynamic, lopsided, and still entirely respectable. In fact, distortion often tells a story. A warped disk, tidal tail, offset bar, or stream of stars can reveal past encounters. Galaxies carry scars, souvenirs, and ongoing paperwork from previous meetings. Some dwarf galaxies orbit larger hosts for billions of years, gradually stripped of stars and gas by tidal forces. Others plunge inward and are absorbed. The Milky Way itself is currently interacting with several dwarf companions, and evidence suggests it has merged with smaller galaxies many times before. Galactic life is social, whether invited or not. Mass is another key trait. Small dwarf galaxies may contain a few million stars. Large spirals hold hundreds of billions. Giants can exceed that comfortably. Yet visible stars tell only part of the story. Dark matter halos surrounding galaxies often contain much more mass than the luminous components. This invisible matter strongly affects motion, mergers, and stability. Two galaxies approaching one another are not merely disks of stars drifting together. Their extended dark matter halos may begin interacting long before bright structures overlap. So when galaxies meet, the visible greeting may be late compared with the gravitational introduction. Size also changes timescales. A dwarf galaxy orbiting a giant may be disrupted relatively quickly by comparison, though quickly still means astronomical patience. Two large spirals of similar mass can engage in prolonged encounters with multiple passes before finally merging. Relative mass influences who is transformed more dramatically. When a small galaxy falls into a much larger one, astronomers often call it a minor merger. The larger system may gain stars, gas, and subtle structural changes, while the smaller galaxy can be torn apart almost entirely. When two galaxies of comparable size merge, that is a major merger. These events can radically reshape both participants, often turning spirals into elliptical-like remnants. Equal meetings tend to rewrite everyone's schedule. Let's visit a few well-known galaxies as characters in our story. The Andromeda Galaxy is a large spiral galaxy, and the nearest major companion to the Milky Way. It contains perhaps around 1 trillion stars by some estimates, though counts vary with methods and assumptions. It is moving toward us and is expected to merge with the Milky Way in several billion years. Andromeda is not hostile. It is simply obeying gravity with commitment. The Triangulum Galaxy, another member of our local group, is smaller and also part of the broader gravitational neighbourhood. Interactions among multiple galaxies and groups are common and complex. Meanwhile, in rich galaxy clusters containing hundreds or thousands of members, galaxies orbit through shared gravitational wells, encounter hot intracluster gas, and undergo repeated interactions. Environment matters enormously. A galaxy in isolation may evolve slowly, conserving gas and structure. A galaxy in a dense cluster may be harassed gravitationally, stripped of gas, or merged over time. Astronomers even use the phrase galaxy harassment for repeated high-speed interactions in clusters, proving once again that science occasionally names things with more personality than expected. Colour tells stories too. Blue galaxies often indicate younger stellar populations and ongoing star formation. Redder galaxies tend to host older stars and less fresh star birth. This is simplification, but a useful one. Spirals are frequently bluer in disks, ellipticals redder overall, so in cosmic portraits colour can hint at age, fuel supply and recent behaviour. Rotation patterns matter as well. In spiral galaxies, stars in the disk move in organised orbits around the centre. In ellipticals, motions are more randomised. This difference affects how systems respond to mergers. Ordered rotating disks can be disrupted. Randomised stellar swarms may absorb newcomers differently. Think of the contrast between a synchronised dance floor and a crowded room where everyone chose their own tempo. Both contain movement. Only one has obvious choreography. There is also the central black hole factor. Many large galaxies host supermassive black holes in their cores. Their masses range from millions to billions of times the mass of the Sun. During mergers, gas can funnel inward, feeding these black holes and igniting active galactic nuclei, extremely bright central regions powered by matter heating as it falls inward. So a galaxy that once looked serene may become brilliantly active during an encounter. Even calm giants can become dramatic when dinner arrives. One reason astronomers care so much about galaxy types is that they are clues to evolution. We do not merely classify shapes for decorative satisfaction. We classify because structure reflects history. A spiral may have preserved gas and rotational order. An elliptical may be the outcome of past mergers and exhausted star-forming fuel. An irregular may reveal disturbance, youth, low mass, or ongoing interaction. Every galaxy is both object and autobiography. When two galaxies approach each other, they bring those autobiographies into contact. A gas-rich spiral meeting another gas-rich spiral can trigger intense starbursts. A giant elliptical swallowing dwarfs may quietly grow larger. A spiral passing too close to a cluster environment may lose gas and slowly fade. There is no single script because galaxies arrive with different sizes, fuels, motions, and memories. That variety is part of what makes the universe so visually rich. If every galaxy were identical, astronomy would still be important, but many telescope posters would become repetitive. Instead, the sky offers pinwheels, golden ovals, broken crescents, compact swarms, dusty bars, tidal tails, and luminous giants. And somewhere among them, our own galaxy continues its orbiting life, carrying the solar system through one spiral arm neighbourhood among many. The Sun circles quietly inside this larger city, taking roughly 230 million years per orbit around the galactic centre. Since the earliest dinosaurs, we have gone around only once or so, which is a graceful reminder that while human calendars feel urgent, galactic calendars are unbothered. For now, keep in mind who the participants are: spirals with young stars and turning disks, ellipticals rich with age and mass, dwarfs that orbit giants, irregulars shaped by circumstance, and quiet giants whose stillness often conceals dramatic histories. When galaxies meet, they do not arrive empty-handed. They bring billions of stars, invisible halos, central black holes, clouds of gas, and the accumulated consequences of everything they have been before. Set aside for a moment the human habit of expecting quick arrivals. We live by clocks, countdowns, delivery windows, meeting times, and the quiet suspicion that if something has not happened in 3 minutes, it may never happen at all. Even patience is often measured in hours. A delayed train feels meaningful. A week can seem long. Waiting for a software update can inspire language unsuitable for polite astronomy. Galaxies do not share these concerns. When two galaxies begin moving toward one another, the approach unfolds across spans of time so large that entire species may appear and vanish, while the distance only modestly changes. What we call an encounter is usually not a sudden event, but a prolonged era. It is less like a crash, and more like a continent drifting toward another continent while stars keep shining overhead. This long approach begins with gravity. Two galaxies may be separated by millions of light years, yet still belong to the same gravitational neighbourhood. If enough mass lies nearby and relative motion is suitable, they become bound to one another. That means they are not simply passing strangers in open space. They are participants in a slow mutual future. Our own cosmic neighbourhood, the local group, contains more than 50 known galaxies, including the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf companions. This is not an isolated arrangement. Galaxy groups are common. Larger clusters contain hundreds or even thousands of galaxies moving within shared gravitational wells. Some systems merge, some orbit for immense periods, some skim past each other and continue on altered paths. Some are slowly stripped of gas and stars by repeated encounters. Space can look empty while remaining socially complicated. Let us focus on a future famous enough to have become popular science tradition, the Milky Way and Andromeda. At present, Andromeda lies roughly 2.5 million light-years away. Light leaving it today takes about 2.5 million years to reach us. In other words, when you look at Andromeda, you're seeing it as it was when early human ancestors were walking Earth. That alone can make a person reconsider what current events means. Measurements show Andromeda is moving toward the Milky Way. More precisely, the distance between us is decreasing due to mutual gravity, overcoming local cosmic expansion at this scale. The expected merger is several billion years away, with first close approach often estimated in around 4 to 5 billion years, though exact numbers evolve with improved data. So yes, something large is coming. No, there is no need to reorganize tomorrow. The long approach of galaxies is governed by a few key ingredients: mass, velocity, direction, surrounding environment, and time so generous it borders on comedy. Imagine tossing two stones across a field. Their paths are mostly straightforward because the field does not bend them much. Now imagine two mountains made of invisible gravity moving through a flexible landscape, where every particle influences every other particle. Their trajectories become more subtle. Galaxies do not move in straight lines for long. As they near one another, gravity curves their paths. If they begin with sideways motion, they may not head directly center to center. Instead, they can sweep past, arc around, and begin long orbital dances. This matters because many galactic mergers involve multiple close passes rather than one decisive moment. The first pass may distort both galaxies dramatically. Then they separate again. Distance grows for a while, but energy has been redistributed. Dark matter halos overlap. Stars and gas have exchanged momentum. The pair may no longer have enough kinetic freedom to escape one another fully, so they return. That returning can take hundreds of millions of years. To human minds it sounds absurd. To galaxies, it barely counts as scheduling. During the approach, visible changes may remain subtle for a long time. If you watched from far away with impossible patience, two spiral galaxies might look mostly normal for ages. Their disks turn, stars orbit, gas clouds form stars. Yet underneath the calm appearance, the gravitational field is changing. Outer stars feel gentle tugs first. Dark matter halos, extended far beyond the bright stellar disks, may begin overlapping before any obvious visual interaction occurs. Since halos contain substantial mass, this invisible stage matters greatly. One could say the unseen parts begin the handshake long before the visible bodies embrace. That is a surprisingly common theme in physics. Consider tides on Earth. The moon raises ocean tides through gravity across distance. No touching required. Likewise, galaxies reshape one another through differential gravitational pull. Near sides feel slightly stronger attraction than far sides. Over time, those small differences accumulate into stretching and distortion. A galaxy can begin changing while still looking serene. There is something calming in that idea. Transformation often starts quietly. Astronomers learn about long approaches through observation and simulation. We cannot watch one merger from start to finish in real time because the universe refuses to respect documentary run times. Instead, we observe many systems at different stages and compare them with computer models. One pair might be just beginning interaction. Another shows tidal tails after a first pass. Another has dual bright nuclei nearing final union. Another has already settled into a merged elliptical remnant. Put together, these snapshots form a narrative. It is cosmic archaeology mixed with forecasting. The antennae galaxies are a famous example of a system mid-merger. Their long tails and active star formations suggest a dynamic interaction already underway. They help astronomers understand what gas-rich spiral collisions can do. Meanwhile, more advanced remnants reveal how chaos gradually becomes a new equilibrium. That phrase, new equilibrium, is useful. Galactic encounters are not endless disorder. They are pathways from one stable arrangement to another, with dramatic intermediate steps. The approach phase also depends on something called dynamical friction. Despite the name, there is no literal rubbing of galaxy surfaces. Instead, as a massive object moves through a background of stars and dark matter, it gravitationally perturbs them, creating a wake of enhanced density behind it. That wake tugs backward on the moving object, draining orbital energy. In simple terms, galaxies moving through each other's halos gradually lose momentum to the surrounding swarm. The result is inward spiraling over time. It is friction made of gravity and statistics rather than surfaces and heat. The universe enjoys reusing words while changing their meaning. Now imagine living on a planet within one of these galaxies during the long approach. For millions of years, the night sky would slowly change. A neighbouring galaxy would grow larger generation by generation. At first, perhaps a faint smudge. Later, a grand, elongated glow. Eventually, a dominating presence with visible structure spanning much of the sky. No one individual would witness the whole progression, but cultures might pass down records, stories, and increasingly accurate maps of the brightening visitor. Think of how humans tracked planets and comets over centuries. Now extend that tradition over millions of years, with a galaxy swelling across the heavens. It would be the longest incoming guest announcement imaginable. Yet even then, local life might continue quite normally for immense periods. Days still follow planetary rotation. Seasons still depend on axial tilt and orbit. Rivers flow, trees grow, civilizations argue over architecture and snacks. The galactic approach changes the larger backdrop before it changes local conditions. This contrast between grand scale and ordinary life is one of astronomy's quiet comforts. Enormous processes can be underway while daily existence remains intimate and manageable. You do not need to solve the merger to make tea. The long approach can also involve more than two participants. Galaxy groups often contain multiple members whose mutual pulls complicate trajectories. A third galaxy may be drawn in later. Dwarf galaxies may be stripped and absorbed during the main event. Streams of stars from previous mergers may already lace the halos. Real systems are often messier than textbook pairings. Even the future of the Milky Way and Andromeda may include contributions from Triangulum and numerous smaller companions. Cosmic stories rarely stay limited to two named characters. Mass ratios matter too. If a small dwarf galaxy approaches a giant spiral, the long approach may end in tidal disruption rather than a balanced dance. The dwarf can be stretched into streams before reaching the centre. Its stars disperse into the host halo. Its identity becomes memory distributed across orbits. Large equal mass spirals, by contrast, can each significantly deform the other. In astronomy, who approaches whom sometimes depends on where you place the centre of mass. Another subtlety is orientation. If two spiral galaxies approach with aligned disks, the encounter may produce different tails and gas flows than if one disk is tilted or rotating opposite relative to the orbital motion. Geometry influences outcome strongly. A slight change in initial angle can rewrite billions of years of visual drama. That is true in many things, though usually with fewer stars involved. The long approach also teaches humility about speed. Galaxies can move hundreds of kilometers per second relative to one another. By human standards, that is astonishing. Yet because distances are so vast, the merger still takes eons. Fast motion plus huge distance equals patient story. We often confuse speed with quick completion. Space regularly corrects that misunderstanding. There is a deeper beauty here as well. The approach is not wasted time before the real event. It is part of the event. Halos interacting, orbits curving, tides beginning, gas responding, trajectories committing. These are not preliminaries, but genuine stages of transformation. We sometimes undervalue slow beginnings because they lack spectacle. The universe does not share that bias. Some of the most consequential processes begin as tiny deviations accumulating over long durations. A star forms from gradual cloud collapse. Mountains rise through patient tectonics. Evolution proceeds through countless generations. Galaxies merge through long approaches where almost nothing seems urgent. Perhaps patience is not delay at all, but a different form of action. As the Milky Way and Andromeda continue their measured convergence, our Sun will also age. In several billion years, the Sun itself will brighten significantly and enter later stellar phases. By the time galaxies seriously interact, Earth's conditions will be profoundly changed for reasons entirely unrelated to Andromeda. This is another favourite cosmic habit. Multiple timelines unfolding simultaneously. While one event approaches slowly, another process may matter sooner. Still, for tonight, we remain with the galaxies, closing distance grain by grain on the scale of light years. Soon enough, gravity's whisper becomes visible stretching. Spiral arms distort. Tidal tails begin to form. Order starts to loosen. But before that first dramatic pass, there is this long, almost meditative interval where two immense systems simply move toward a shared future neither can avoid. For now, picture Andromeda hanging faintly in a dark sky, a remote island of stars. Picture the Milky Way turning quietly around us. Between them lies millions of light years of space, already shrinking, already reshaping destiny one patient kilometre at a time. Far before any bright arms twist together, before streams of stars arc into space, before gas clouds ignite in crowded bursts of new light, something quieter begins. It starts in silence so complete that no ear could notice it, no eye could catch it, and no ordinary clock would think to mark the moment. Two galaxies, still separated by enormous distance, begin to feel each other. This first contact is not touch. It is gravity. That word is familiar enough to seem simple. We use it daily. Gravity keeps feet on floors, rain falling downward, cups committed to tables unless dramatically interrupted. It guides the Earth around the Sun, the Moon around Earth, and satellites around both physics and bureaucracy. Yet gravity on galactic scales becomes something harder to feel intuitively. It is not just a downward pull. It is relationship across distance. It is geometry shaping motion. It is the reason islands of stars can spend billions of years apart and still be destined to meet. When two galaxies begin their long approach, gravity speaks first through tiny changes. A star on the outer edge of one galaxy may continue orbiting its centre, much as before, but not exactly as before. Its path bends by a minute amount. Gas clouds drift slightly off their previous routes. Dark matter particles within the halo respond collectively. The entire system remains recognisable, but every orbit has gained a faint new influence. This is how many large transformations begin, almost invisibly. Suppose you could watch the Milky Way from far outside with time sped up enough for millions of years to pass like weather. At first, it would rotate in familiar grace, spiral arms turning, stars tracing paths around the centre. Nearby, the Andromeda Galaxy would do the same. Each galaxy would seem self-contained, a world unto itself. Then gradually, trajectories would no longer look perfectly independent. Outer regions would begin to lean, not dramatically. No sudden lurch, no cinematic alarm bells. More like two dancers across a large room noticing each other and adjusting their steps long before meeting at the centre. This early stage can be difficult to appreciate because human senses prefer obvious events. We notice bangs, breaks, starts, and endings. We are less gifted at perceiving cumulative nudges, but the universe often favours nudges. Enough of them, sustained long enough, can reorganise almost anything. Gravity weakens with distance, yes, but it never becomes irrelevant simply because something is far away. Double the distance and the force drops sharply. Yet if the masses involved are galaxies containing hundreds of billions of stars and enormous halos of dark matter, even a weak pull matters over time. Time is gravity's favourite ally. A brief, weak force may seem negligible. A weak force acting for hundreds of millions of years becomes architecture. That principle applies everywhere. Ocean tides reshape coasts. Repeated footsteps wear paths into soil. Small habits alter lives. Galaxies too are edited by persistent influence. Now add dark matter to the story. Most of a galaxy's mass is not invisible stars. Observations suggest galaxies sit within extended halos of dark matter, unseen material inferred from gravitational effects. These halos stretch far beyond the bright disks visible in photographs. So when two galaxies approach, their invisible outskirts may begin overlapping long before their luminous stars appear close. In that sense, the first whisper between star cities is often carried by what we cannot see. The visible spiral arms are merely the bright downtown districts. The real gravitational reach extends much farther. Imagine two nations whose suburbs span continents, while their city centres remain distant. Administrative boundaries would become very interesting. Astronomy specialises in scales that make ordinary metaphors wobble. As halos interact, they alter the motions of stars and gas embedded deeper within each galaxy. The overall gravitational potential changes. Orbits that were nearly circular may become slightly elongated. Resonances can develop. Bars within spiral galaxies may strengthen. Gas can begin moving inward or outward depending on the details. None of this requires direct collision. No star has to strike another star for a galaxy to start changing. That remains one of the most surprising truths of galactic encounters. The drama comes less from impact than from revised motion. If two galaxies were somehow made of compact solid matter, meetings would be brief and catastrophic. Because they are diffuse systems dominated by space and governed by long-range gravity, meetings are prolonged and intricate. This early whisper also creates asymmetry. The near side of a galaxy feels a slightly stronger pull from the approaching companion than the far side does. That difference in force across the galaxy is called a tidal effect. We know tides from Earth's oceans, raised largely by the moon and the sun. On galactic scales, tides can stretch entire stellar disks. At first the distortion is subtle. Outer arms may become uneven. A disk may warp slightly. The centre may remain calm while the outskirts begin to notice something incoming. It is often the edges of systems that sense change first. There may be a life lesson hiding there, but tonight we'll stay with astronomy. Gas responds differently from stars. Stars mostly follow gravitational orbits as individual bodies. Gas behaves collectively. It can compress, shock, dissipate energy, and flow. So even a modest gravitational disturbance can start rearranging gas clouds in ways that later become spectacular. Clouds may crowd into spiral arms. Central regions may gain fresh inflow. Dormant star-forming zones may receive new pressure. What looks like a whisper now may become a blaze later. This is why astronomers pay close attention to seemingly mild distortions in galaxies. A lopsided disk, a warped edge, an offset bar, unusual gas motion. These can be early evidence of interaction. The galaxies are not yet entwined, but the conversation has begun. Telescopes tuned to different wavelengths help reveal it. Visible light shows stars. Radio observations can trace neutral hydrogen gas far beyond bright stellar disks. Infrared can peer through dust. X-rays can reveal hot gas and energetic centers. Each wavelength adds a line to gravity's transcript. Sometimes a galaxy that looks peaceful in visible light turns out to have extended gas streams already tugged by a companion. Sometimes a bright central burst hints that interaction has started funneling material inward. Sometimes faint stellar streams mark the remains of smaller neighbours already partially absorbed. Galaxies are excellent at appearing composed while undergoing significant internal revisions. That too may feel oddly familiar. Consider our own neighbourhood again. The Milky Way is not a static object waiting politely for Andromeda. It is already interacting with smaller companions such as the Large Magellanic Cloud and Small Magellanic Cloud. Stellar streams from past mergers arc through the galactic halo. The disk may show ripples linked to previous encounters. Even before the great future meeting, our galaxy has a social history. No major galaxy is an untouched island. Another important effect in this whispering stage is dynamical friction. Despite the name, nothing is scraping. A massive galaxy moving through another's halo gravitationally stirs particles into a denser wake behind it. That wake then tugs backward on the moving galaxy, gradually robbing orbital energy. Picture a boat making waves, except the water is stars and dark matter, and the wake politely slows the boat over hundreds of millions of years. This process helps galaxies lose energy and spiral closer together over time. Without it, some close passes might remain temporary flirtations. With it, long relationships become mergers. One can also ask what it would look like from a planet inside one of these galaxies. For ages, perhaps very little would seem urgent. A neighbouring galaxy in the sky might brighten over geological timescales. Careful astronomers of distant civilizations could chart changing size and motion, generation after generation. Yet daily life under a local sun might remain ordinary. Morning would still depend on planetary rotation, not galactic romance. Rain would still fall according to atmosphere, not Andromeda. Bread would still overbake if forgotten. This contrast is worth enjoying. Cosmic significance and everyday routine often coexist peacefully. You can inhabit a galaxy beginning to merge and still need to tidy the kitchen. There is comfort in that. Sometimes we imagine big future events as things that erase the present. Astronomy suggests otherwise. Huge processes may unfold while local life continues in manageable detail. The whisper stage also reminds us that visibility is not the same as importance. Humans naturally prioritize what can be seen clearly and immediately, but much of the universe's real work happens gradually, invisibly, and through relationships rather than collisions. Gravity has no colour, no sound, no scent, yet it shapes galaxies. As the pull grows stronger, distortions will become easier to notice. Spiral arms may lengthen. Material may begin drawing outward into bridges and tails. Gas clouds may bunch and ignite. Central black holes may one day receive new fuel. But all that later spectacle depends on this earlier murmur. Before there are fireworks, there is mathematics. Before there are tidal tails, there are tiny altered orbits. Before two star cities seem to meet, they begin by changing each other from afar. Perhaps that is why this stage feels so elegant. It asks us to value beginnings that do not announce themselves. It shows that influence can precede contact. It suggests that distance does not mean isolation. Even separated by millions of light years, galaxies can already be participating in each other's future. Imagine standing beneath a clear night sky and trying to count how many stars appear above you. Even away from city lights, the visible number is modest compared with reality, but it still feels abundant. The sky suggests crowding. Tiny points of light seem scattered everywhere. Constellations connect them. The Milky Band stretches overhead like spilled brightness. It is easy to conclude that space must be busy, packed, and full of objects nearly touching. That impression is understandable. It is also gloriously misleading. One of the strangest truths about galactic collisions is that when two galaxies pass through one another, almost no stars actually hit. Hundreds of billions of stars may participate in the larger encounter, yet direct stellar crashes remain extremely rare. At first, this sounds impossible. If two swarms each contain so many stars, how could impacts not be common? Surely somewhere suns should be colliding like marbles poured into a bowl. The answer is simple in principle and astonishing in scale. Space inside galaxies is mostly empty. We touched on this earlier, but now it deserves a slower look. Stars are large objects, yes, but the distances between them are so vast that their physical sizes become tiny targets in enormous volumes. Our Sun is about 1.39 million kilometers across. That is genuinely immense by local standards. Yet the nearest known star, Proxima Centauri, lies more than 4 light-years away. To compare those numbers directly is almost rude. It is like comparing a grain of dust to the width of an ocean. If the Sun were reduced to the size of a small coin, the nearest star might still be thousands of kilometers away depending on the scaling used. You could place one coin in one country and another coin in a distant country, then say, "Be careful, they might collide." This is the geometry galaxies work with. Stars are not packed like stones in a wall, they are more like isolated lanterns hung across a continent of darkness. So when two galaxies merge, their stars usually pass through one another's neighbourhoods without direct contact. Paths are altered, orbits are rewritten, structures are transformed, but physical star-to-star impact is extraordinarily unlikely. This reveals something important about language. When we say galaxies collide, we are describing systems colliding, not individual stars smashing together in great numbers. The galaxies as organised gravitational communities overlap and merge. Their residents mostly keep respectful distance. Even on the busiest galactic streets, stars are committed to personal space. There are denser regions, of course. Near galactic centres, especially around bulges or nuclear star clusters, stars can be packed much more closely than in outer spiral disks. Globular clusters also contain high stellar densities. In such places, close encounters become more likely, and rare direct collisions can happen over long timescales. But more likely in astronomy often means still uncommon, just less absurdly uncommon. The typical star in a galaxy spends its life not colliding with anything. Instead, stars interact through gravity. That distinction matters. Two stars can pass relatively near one another without touching, and still significantly influence each other's paths, especially if the encounter is close enough. Planetary systems may be perturbed. Oort cloud-like comet reservoirs may be disturbed. Orbits can shift. So while stars seldom crash, they can still inconvenience each other. The universe often prefers subtle disruption over dramatic destruction. Let's imagine two spiral galaxies approaching. Their luminous disks begin to overlap. From far away, the sight is magnificent. Arms tangled, dust lanes crossing, light concentrated in twisting forms. Inside the merger, however, a typical star experiences mostly empty travel. If you rode along with such a star, admittedly a long commute, you would likely pass through vast darkness. Another star might appear brighter than usual at some stage if it came relatively nearby, but nearby could still mean trillions of kilometres. There would be no bumper-to-bumper traffic, no sudden metallic crunch, no celestial insurance paperwork. This surprises us because photographs flatten depth. A galaxy image compresses three-dimensional space into a two-dimensional picture. Thousands or millions of stars may seem stacked close together, but they are often separated by huge distances along the line of sight. The night sky does this too. Constellation stars can appear side by side while actually lying vastly different distances from Earth. Our eyes are talented at seeing patterns, less talented at judging cosmic depth. Another reason stellar collisions are rare is that stars themselves are small relative to their gravitational spheres of influence. A star's light and gravity reach far, but its physical body occupies a tiny region. Hitting the star itself requires extraordinary precision. It is rather like throwing darts across continents and expecting them to strike grains of rice. Now, when direct collisions do occur, they can be spectacular. Two stars merging may produce unusual objects such as blue stragglers in clusters. Compact remnants like neutron stars colliding create gravitational waves and heavy elements such as gold and platinum. White dwarf mergers can trigger certain supernovae under the right conditions, so stellar collisions are scientifically important. They are simply not the main story in galaxy mergers. The main story is orbital rearrangement. As galaxies pass through each other, stars respond to the combined gravitational field. Some are flung into long tidal tails. Some sink inward statistically as energy redistributes. Some move into more randomized orbits. Some remain broadly in place but within a changing system. Imagine two schools of fish passing through one another, except every fish affects every other through invisible attraction, and nobody physically bumps unless exceptionally unlucky. Even that understates the emptiness. Gas behaves differently, which is why people sometimes confuse the issue. Interstellar gas clouds are spread out and can collide, compress, shock, and cool. Dust mixed with gas can absorb and re-radiate energy. These interactions trigger bursts of star formation. So when astronomers observe intense activity in merging galaxies, much of it comes from gas dynamics, not suns smashing together. New stars may be born because old stars politely missed each other. That is a wonderfully indirect universe. Our own Milky Way and the Andromeda Galaxy are expected to merge in several billion years. This future event often inspires concern about the solar system. Will the Sun hit another star? Almost certainly not. Could the solar system's orbit around the galactic centre be changed? Yes. Could nearby stellar encounters become more probable than today, over immense timescales? Potentially. Could Earth face problems from the merger itself before any stellar collision? Those would more likely involve long-term orbital relocation within the merged galaxy, radiation environment changes from active galactic centres, or entirely separate issues related to the Sun's own evolution. But a head-on Sun versus random star crash is not the expected headline. Again, the danger in space is often not impact, but environment. Even in our present galaxy, stars move around the centre with differing speeds and paths. Yet the disk remains stable because distances are huge and orbits are coordinated statistically. If stars were close packed, galaxies would be chaotic wrecks. The fact that galaxies persist for billions of years is evidence of spacious design by physics rather than crowded catastrophe. There is also a deeper lesson about scale and intuition here. Humans evolved in dense environments of surfaces, fluids, walls, trees, weather, and nearby objects. In our world, collision is common. We drop things. We trip over furniture. We bump into doors while carrying laundry and pretending it was strategic. So we instinctively imagine the universe in similar terms. But the cosmos is not built at household scale. At cosmic scale, emptiness dominates. Distances become the main architecture. Motion occurs through vast volumes where contact is rare and gravity does most of the organising. It takes effort to think that way, because nothing in daily life prepares us for it. Perhaps that is why astronomy feels refreshing. It repeatedly introduces realities that ignore our instincts with complete confidence. Consider the centre of some galaxies, where stars orbit close to supermassive black holes such as Sagittarius A star. Even there, where speeds are high and stellar densities rise, stars still mostly avoid collisions. They whirl through intense gravitational environments while maintaining surprising separation. Nature appears committed to giving stars room. Of course, room does not mean loneliness. Stars belong to systems. They orbit shared centres, live in clusters, enrich gas with heavy elements, host planets, and influence neighbours over time. They are participants without needing contact. There is something elegant in that. Major change can happen through alignment, pull, and timing rather than direct impact. Galaxies merge. Structures dissolve and reform. New generations of stars ignite. Central black holes may eventually spiral together, yet the stars themselves, by and large, pass one another in silence. No clang, no fireball, just altered futures. This can feel strangely comforting. We often imagine transformation as something violent and immediate. Astronomy offers another model: vast reorganization through mostly non-contact processes, guided by invisible relationships and patient motion. Even two galaxies can pass through each other without widespread crashing. Perhaps not every meeting needs destruction to create something new. Picture billions of stars crossing through another galaxy's domain like travelers in a dark open landscape, each far from the next, each following gravity, each missing almost everyone, and yet together helping remake the entire sky. Long before a galaxy loses its recognizable shape, there comes a moment when symmetry begins to fail. Nothing shatters. No alarm sounds across the stars. Spiral arms do not suddenly snap loose and go wandering into space like misplaced ribbons. Instead, the edges start to respond unevenly. One side is tugged a little harder than the other. Outer stars drift from their older paths. Gas clouds begin gathering where they did not gather before. A graceful disk that once seemed balanced starts leaning into a new geometry. This is the work of tidal forces. The term may sound coastal, and in a sense it is. On Earth, tides are caused mainly by the gravitational pull of the Moon, with assistance from the Sun. The side of Earth nearest the Moon feels a slightly stronger pull than the centre does, and the far side feels slightly less. That difference stretches the oceans into bulges. Water rises and falls not because the Moon grabs one sea like a spoon, but because gravity varies across distance. Now enlarge the idea until oceans become galaxies. Replace coastlines with spiral arms. Replace beaches with billions of stars. Replace one planet with 2-star cities crossing the dark. Tidal forces in galactic encounters come from the same principle. The near side of one galaxy feels stronger attraction from the other galaxy than the far side does, since a galaxy is enormous, spanning tens or hundreds of thousands of light years. Even a modest gradient in gravity across that size can matter tremendously over time. And time, as always, is willing to help. If a galaxy were a rigid object, it might resist with a single body response. But galaxies are not rigid. They are loose gravitational communities of stars, gas, dust, and dark matter. Their members orbit within shared structure. Give different regions slightly different pulls, and the structure can be stretched, twisted, warped, and partially rearranged. That is why tidal forces are among the first visible signatures of a galactic encounter. A spiral disk that once looked calm may begin to show asymmetry. One arm grows longer, another thickens. Outer material starts streaming outward. A bridge of stars and gas may form between the galaxies. What seemed stable becomes expressive. There is something almost elegant about that. The universe does not always announce change through explosion. Sometimes it announces change through distortion. Picture two spiral galaxies approaching one another. At large distance, each rotates in relative independence. Stars orbit their own centres. Gas traces familiar patterns. Dark matter halos overlap invisibly in the background. Then comes a closer pass. As they sweep by, each galaxy exerts a stronger pull on the other's near side. Outer stars are easiest to influence because they are less tightly bound than stars deep in the core. Those outskirts begin to stretch outward, creating long tidal tails, vast streams of stars and gas drawn into space. These tails can extend hundreds of thousands of light years. That means a temporary feature of a merger can become larger than many entire galaxies. Astronomy enjoys making side effects enormous. Some stars in a tidal tail may remain gravitationally linked, and later fall back inward. Others may become part of extended halos. In some cases, dense clumps within tails can collapse into new dwarf galaxies called tidal dwarf galaxies, assembled from recycled material flung outward during the encounter. Even discarded structure can become architecture. Gas within these stretched regions behaves differently from stars. Gas clouds can compress, collide, cool, and fragment. So tidal disturbances often help trigger star formation. Bright knots of young stars may appear in tails and bridges, making these features glow with fresh blue light. What began as gentle, uneven pulling can end in stellar nurseries. The famous antennae galaxies are one of the best-known examples. Their name comes from the two sweeping tails extending from the merging pair, resembling insect antennae. Those tails are tidal features, matter pulled outward by gravitational interaction. They are not debris from stars smashing together, they are signatures of orbital rewriting. Another remarkable system is Whirlpool Galaxy, often called M51, interacting with a smaller companion. The grand spiral structure we admire may be enhanced and maintained in part by that encounter. A nearby companion can stir density waves, sharpen arms, and reorganize gas flow. Sometimes, a galaxy's beauty is collaborative. Tidal forces also create bridges. As galaxies pass near one another, material can be drawn out between them, forming luminous connectors of stars and gas. These bridges are temporary but dramatic, like cosmic causeways suspended between star nations. No engineer approved the design. Gravity simply improvised. Why are outer regions more affected than inner cores? Because stars near the centre of a galaxy are often more tightly bound by the concentrated mass there. Their orbital speeds are high, and the local gravitational grip is stronger. Outer stars feel weaker binding, so external tides can tug them more effectively. This creates a common pattern. Cores survive relatively intact early on, while outskirts become theatrical first. That pattern appears in many systems, not only galaxies. The loosely held parts of anything tend to move first. Dark matter halos participate too, though invisibly. Since halos extend far beyond visible disks, they can be stretched and overlap substantially during encounters. Their changing mass distributions influence how stars and gas respond. Even when we cannot see the halo itself, we see its fingerprints in the motion of visible matter. Once again, unseen structure matters deeply. Tidal forces do not only make tails, they can also warp disks. A galaxy seen edge-on may develop bends or ripples. Its once flat stellar plane becomes slightly twisted. Gas layers may buckle. Bars in central regions can strengthen as gravitational torques redistribute angular momentum. A torque is a twisting influence that changes rotational motion. In galaxy encounters, tidal torques can funnel gas inward toward galactic centers. That inward gas flow is important. When large amounts of gas move toward the core, it can ignite central starbursts or feed a supermassive black hole, turning a previously quiet nucleus into an active galactic center. So the same encounter that stretches stars outward may simultaneously drive gas inward. The universe often solves one problem by creating two dramatic directions at once. There is no single tidal outcome because geometry matters enormously. If two spiral galaxies approach face-on, one pattern emerges. If one disk is tilted sharply, another appears. If their relative motion is faster, tails may be shorter or weaker. If masses differ greatly, the smaller galaxy may be more strongly distorted. Tiny changes in orientation at the start can lead to strikingly different visual endings. This is why astronomers run many simulations. By adjusting masses, trajectories, gas fractions, and angles, they reproduce real, observed systems and infer what likely happened. A galaxy snapshot is a clue. Simulation helps supply the verbs. Now imagine witnessing this from a planet within one of the galaxies. The process would be slow beyond ordinary comprehension. No one generation would watch a tail grow from nothing to full span in real time. But over long ages, careful sky records might reveal neighbouring stars shifting subtly, bright structures enlarging, a companion galaxy stretching across the heavens, new luminous arcs appearing where none existed before. Civilizations could rise beneath a changing sky and never know they were living through tides of stars. That thought carries a certain calm. Great transformations may occur so gradually that life still unfolds in daily rhythms beneath them. Breakfast remains breakfast, even during a merger. Tidal forces also help explain why many large elliptical galaxies likely formed from past spiral mergers. Repeated stretching, orbital scrambling, and energy redistribution can erase neat disks and ordered arms. After enough interaction, what remains may be a smoother, rounder stellar system with randomized stellar motions. The tails fade, the bridge disperses, the old spirals become memory. What looks serene later may have been dramatic earlier. This is a useful reminder whenever we encounter calm surfaces. Astronomers sometimes find faint shells or streams around galaxies, subtle arcs of stars left over from previous tidal interactions. These are like archaeological traces of old encounters. A galaxy may appear settled, yet careful imaging reveals lingering evidence of past stretching. Space keeps receipts. There is also something philosophically pleasing about tides on every scale. The moon lifts oceans, galaxies lift stars. Gravity, acting differently across distance, creates patterns from fluid water and from stellar swarms alike. The same principle that moves a harbour tide can reshape a galaxy. Physics often repeats itself with upgraded scenery. During the Milky Way's future encounter with the Andromeda Galaxy, tidal forces are expected to dramatically distort both systems. Long streams may form, stellar orbits will change, gas flows will ignite activity. Over time, both spirals may lose their classic forms and settle into a larger merged remnant, sometimes informally nicknamed Milkomeda. The name sounds cheerful for such a grand rearrangement. Yet even then, most stars still will not collide directly. Tides do the sculpting through differential gravity, not widespread impacts. That remains the key insight. Galaxies bend because different parts are pulled differently. Not everything inside a galaxy behaves like a star. Stars are compact, self-contained, and mostly content to follow orbital paths for immense stretches of time. They move through mergers like seasoned travellers carrying their own gravity with them. Gas and dust are another matter entirely. They are diffuse, responsive, easily crowded, easily compressed, and wonderfully dramatic when disturbed. So when two galaxies begin to stretch, bend, and overlap, some of the brightest consequences come not from old stars colliding, but from restless clouds finally being pushed together. This is where rivers of gas begin to matter. A spiral galaxy often contains enormous reserves of hydrogen gas, mixed with helium and traces of heavier elements. Much of it is thinly spread through the disk. Some lies in giant molecular clouds, cold, denser regions where stars can eventually form. Dust, made of tiny grains of carbon-rich or silicate material, drifts among the gas. Though dust is only a small fraction of the total mass, it plays an outsized role by helping clouds cool and by blocking or scattering starlight. In calm times, this material circulates through the galaxy in relatively stable patterns. Clouds form, clouds disperse, stars are born, old stars die and return enriched matter to space. It is a long recycling system run with admirable patience. Then another galaxy arrives. The moment tidal forces begin reshaping orbits, gas notices quickly. Unlike stars, gas clouds can crash into other gas clouds. They can pile up. They can lose energy through radiation. They can shock, compress, fragment, and flow inward or outward depending on the geometry of the encounter. A star may glide past disruption. Gas tends to get involved. Imagine two weather systems meeting over an ocean. Air masses twist, pressure changes, fronts develop, clouds gather, storms organize. Now replace air with interstellar hydrogen spanning thousands of light years, and replace weather with gravity. That gives the general mood. As galaxies pass close, streams of gas may be pulled into bridges between them. Other gas is flung into tidal tails stretching far into space. Some is driven toward galactic centers. Along the way, clouds collide at speeds high enough to create shock waves, heating the material before it cools again. Cooling is important. hot gas resists collapse. Cooler gas can condense into denser clumps. Dust helps this process by radiating energy away in infrared wavelengths. Once enough mass gathers in one region, gravity takes over locally and pulls the cloud inward. This is how starbirth begins. The cloud collapses into fragments. Dense cores form. Protostars ignite. Nuclear fusion starts. New stars enter the galaxy, often in groups. During a merger, this can happen on extraordinary scales. Astronomers call such episodes starbursts, periods when galaxies form stars far faster than usual. A system that once produced a modest number of new stars each year may suddenly create many times more. The galaxy brightens. Blue-white young stars appear in clusters. Ultraviolet radiation floods nearby gas. Supernovae will later follow as the most massive of these newborn stars live fast and die quickly. So a collision that sounds destructive can become a cradle. One of the best-known examples is the Antennae Galaxies. These two galaxies, caught in a long merger, display spectacular tidal tails and numerous bright star-forming regions. Observations show clusters of young stars packed into turbulent zones where gas has been compressed by the interaction. They are not unusual because they are colliding. They are famous because we can see the process so clearly. Another class of objects, called ultraluminous infrared galaxies, often owe their brightness to mergers as well. These systems can shine intensely in infrared light. Because dust absorbs radiation from hidden starbursts and active galactic centers, then re-radiates that energy at longer wavelengths. To visible eyes, parts may look obscured. To infrared telescopes, they can blaze. This is one reason astronomy uses many wavelengths. A galaxy may seem calm in optical light while dust hides furious activity within. Radio, infrared, ultraviolet, and X-ray observations reveal chapters the visible spectrum politely omitted. There is a useful contrast here. Old stars tell us where a galaxy has been. Gas tells us what it might become. When gas is stirred, the future changes. Consider our own Milky Way. It still forms stars today, though not at starburst levels. Clouds within spiral arms continue producing new systems. Regions like the Orion Nebula offer nearby examples of stellar nurseries. Yet if the Milky Way were to strongly interact with another gas-rich spiral, rates of star formation could rise dramatically during certain phases of the encounter. The future meeting with the Andromeda Galaxy may include such episodes, though by then both galaxies may have used up much of their easily available cold gas compared with their younger selves. Even galaxies age out of youthful exuberance. Timing matters. In the early universe, galaxies often contained more gas than many do today. Mergers back then may have triggered especially intense starbursts, helping build stellar populations rapidly. The cosmos in its youth was richer in raw fuel and somewhat more willing to make a scene. Modern galaxies can still burst into life, but many have become more measured. Dust deserves a closer look because it sounds trivial and is not. Interstellar dust grains form in the outflows of dying stars and supernova ejecta. They are tiny, but collectively they shape galactic ecology. Dust shields molecular clouds from harsh radiation, allowing cold, dense regions to survive. It provides surfaces where molecules can form. It dims and reddens background starlight. It helps clouds cool. Without dust, star formation would proceed differently and often less efficiently. So when galaxies merge and dust lanes twist through compressed gas, those dark-looking regions may actually be future star factories. Some of the brightest things begin hidden. As new stars ignite, they rarely form alone. Giant clouds fragment into clusters containing dozens, hundreds, or thousands of stars. In violent starburst regions, especially massive compact clusters can form, possible young cousins of ancient globular clusters. Picture entire neighbourhoods of suns switching on within a relatively short cosmic interval. That is not subtle. Massive newborn stars also reshape their surroundings quickly. Their radiation ionizes nearby gas, making nebulae glow. Stellar winds blow cavities into clouds. Later, supernova explosions drive turbulence and spread heavier elements into the interstellar medium. So a merger-triggered starburst is not merely extra star formation. It is a cascade of feedback processes altering the galaxy's gas supply and future potential. The galaxy briefly becomes both nursery and construction site. There is, however, a limit. Starbursts consume gas rapidly. They can also heat or expel gas through winds driven by supernovae or active black holes. This means a merger may trigger brilliant creation for a time, then help exhaust the very fuel needed for future starbirth. The same event that ignites abundance can hasten quiet years later. Nature likes mixed outcomes. Galactic centers are especially interesting during these phases. Gravitational torques can funnel gas inward toward the nucleus. There it may feed a supermassive black hole, creating an active galactic nucleus or quasar-like episode if conditions are right. Now the galaxy may host two forms of brilliance at once: widespread starbirth and a fiercely luminous core powered by accretion. A merger can turn a peaceful spiral into something far more energetic than its earlier self. If you lived on a planet within one of these galaxies during such times, what would you notice? From a local sky, perhaps brighter star-forming regions, altered appearance of the companion galaxy, more prominent nebulae in some directions, and over long timescales a changing stellar backdrop. Yet most daily life would still depend on the local star, planet, atmosphere, and whether someone remembered to repair the roof. Even under cosmic fireworks, chores remain resilient. There is comfort in that too. Large processes do not erase ordinary rhythms immediately. Another beautiful consequence of merger-driven star formation is chemical enrichment. Massive stars forged in starbursts live short lives and explode as supernovae, scattering oxygen, silicon, iron, and other heavy elements. Those materials later become parts of new stars, planets, moons, rocks, oceans, and perhaps listeners wandering about galaxies late at night. The atoms of future worlds may be minted in turbulent merger zones. This makes collisions strangely intimate. What happens between distant galaxies can influence the ingredients of future life elsewhere. Astronomers study gas motions carefully, using radio lines from hydrogen and molecules such as carbon monoxide. These measurements trace inflows, outflows, rotating disks, and compressed clouds. Simulations help explain how orbital geometry channels gas into bars, rings, or central reservoirs. Again, the visible spectacle is only half the story. Beneath the light is fluid dynamics on scales that make weather maps blush. There is also a gentle philosophical point here. Stars seem permanent because they shine steadily for long ages. Gas seems vague because it is diffuse and hard to see. Yet during times of change, the diffuse material often becomes the decisive ingredient. What looked insubstantial becomes transformative. Clouds become suns, dust becomes planets. Thin rivers of hydrogen become the next generation of light. Somewhere inside every galaxy merger, while tidal tails stretch across hundreds of thousands of light years and new stars ignite in crowded nurseries, there may also be something much smaller happening quietly on a rocky world. A tide moves along a shore, wind passes through trees, clouds gather over mountains. Someone looks up at a sky that is slowly changing. This contrast is worth holding on to. When we speak about galaxies colliding, it is easy to imagine that everything inside them is thrown immediately into chaos. Yet galaxies are so large and planetary systems so comparatively tiny that local worlds often continue their own stories, while the larger structure rearranges around them. So what happens to planets during a galactic encounter? The short answer is usually less dramatic than expected. The longer answer is far more interesting. Let us begin with scale. A galaxy may be 100,000 light-years wide or more. A planetary system, by comparison, occupies a minute region around a single star. Even the orbit of Neptune is tiny against galactic dimensions. The distance between stars is immense, and the space occupied by planets around any one star is smaller still. That means most planets are not directly struck by anything during a merger. No passing galaxy sweeps planets off their surfaces like crumbs from a tablecloth. No universal hand reaches in and shakes every orbit loose at once. The galaxy changes at large scale first. Stars move on altered galactic paths. Gas flows inward or outward. New stars form. Tidal streams develop. Meanwhile, many planetary systems remain gravitationally bound to their own stars, continuing local orbits much as before. If you lived on a planet orbiting a typical star in one of two merging galaxies, daily life might remain ordinary for a very long time. Sunrise would still depend on planetary rotation. Seasons would still depend on axial tilt and orbit. Weather would still answer mostly to atmosphere, ocean, land, and the local star. The sky, however, might become extraordinary. A companion galaxy approaching over millions of years would gradually grow brighter and larger. What began as a faint patch could become a dominating structure spanning vast portions of the heavens. Spiral arms might become visible. Later, streams and arcs of stars could appear as the two systems distort each other. Entire civilizations could rise and fall beneath that changing backdrop. Astronomy classes would become increasingly well attended. Still, while most planets remain with their stars, there are several ways galactic encounters can matter locally. The first is stellar flybys. Although direct star collisions are extremely rare, close passes between stars become somewhat more likely in disturbed or denser environments. Close, in this context, may still mean thousands of astronomical units, very far by human standards but near enough gravitationally to perturb distant comet reservoirs or the outer architecture of planetary systems. Our own solar system likely possesses a distant cloud of icy bodies called the Oort cloud. A passing star need not approach the planets themselves to stir that outer region. If enough icy bodies are nudged inward, inner planets could face increased comet activity over long time scales. So one planetary effect of a merger may be indirect, not stars crashing into planets, but altered traffic from distant frozen debris. The second effect is orbital migration within the galaxy. A star may survive the merger perfectly well, yet end up in a different galactic neighbourhood. Its orbit around the merged galaxy's centre can be changed significantly. A star once in a quiet outer disk might move to a more elliptical path passing through denser regions. Another might be flung farther outward into a halo. For the planets around that star, local gravity from the host star still dominates overwhelmingly, yet the broader radiation environment, nearby stellar density, and long-term exposure to certain hazards may change. In other words, your house may stay intact while the district gets rezoned by gravity. The third effect involves star formation. Galactic encounters often trigger bursts of new stars as gas clouds compress. Many of these newborn stars are massive, bright, and short-lived. Massive stars emit strong ultraviolet radiation and later explode as supernovae. If a planetary system lies near such regions, radiation and energetic events may affect atmospheres or biospheres. Location matters greatly. A planet far from active starburst zones may notice little beyond a prettier sky. A planet embedded near vigorous stellar nurseries may face a noisier cosmic neighbourhood. This is true even outside mergers. Galactic geography has consequences. The fourth effect concerns active galactic nuclei. When mergers funnel gas towards central supermassive black holes, those black holes can become highly luminous as matter heats during accretion. An active nucleus may emit intense radiation across multiple wavelengths. If your star system resides near the centre of such a galaxy, conditions may become significantly harsher than in calmer eras. Farther out, the effect weakens. Again, distance is the main architect of safety. Our Sun sits in a relatively ordinary region of the Milky Way, not near the central black hole Sagittarius A star. That separation has likely been helpful. Now let us ask the question many people secretly mean. what about Earth during the future Milky Way encounter with the Andromeda Galaxy? The answer begins with timing. The major interaction is expected billions of years from now. By then, the Sun itself will have evolved substantially. Long before the galaxies fully merge, solar brightening is expected to profoundly alter Earth's habitability. In later phases, the Sun will expand into a red giant. So for Earth specifically, the Sun is likely the more immediate long-term concern than Andromeda. This is a useful cosmic perspective. Sometimes the local star matters more than the incoming galaxy. Still, if one imagines a surviving future Earth-like world elsewhere in the solar system, the galactic merger would probably transform the sky dramatically while leaving planetary orbits around the Sun mostly intact. The Sun might end up on a new path through the merged remnant galaxy. Our night sky could display streams of stars, a brilliant distorted Andromeda Milky Way structure, and perhaps denser stellar vistas in some directions depending on final location. It would be the greatest sky show no one should rush. There is another possibility: rogue planets. Some planets are ejected from their home systems by gravitational interactions over time. In mergers, if stellar encounters perturb planetary systems strongly enough, some worlds may be cast into interstellar space. These free-floating planets would wander the galaxy without a parent star. Cold, dark, and difficult to cheer up. Yet even rogue planets may retain internal heat or thick atmospheres under some circumstances. The universe rarely stops at one category when three will do. Moons would face similar logic to planets. If the host planet remains bound to its star and retains its own system, moons continue orbiting planets unless local disturbances become extreme. The galactic event does not automatically strip moons from worlds. A merger is too large-scale to care about most moon schedules. One of the most important lessons here is hierarchy of gravity. For a planet, the host star dominates. For a moon, the planet dominates locally. For a star, the galaxy shapes broader motion. For a galaxy, the group or cluster matters. Different scales rule different structures. This is why galaxies can collide while planetary systems remain stable. The larger structure changes without necessarily overwhelming the smaller nested systems inside it. Nature is full of such layered organization. A city can be rebuilt while a house remains standing. A continent can drift while a forest grows quietly. A galaxy can merge while a planet still has seasons. There is comfort in that. We often imagine large change as universally catastrophic, but many systems are resilient because they are governed locally. Even if the cosmic map is redrawn, your sunrise may still arrive. Could life survive a galactic merger? Certainly in principle, yes. If a planet avoids harmful nearby events and remains in a stable, habitable environment around its star, there is no reason life must vanish simply because galaxies are merging. Indeed, if intelligent beings existed somewhere during such an era, they might inherit the most spectacular astronomy imaginable. They would watch another galaxy fill the sky, observe tidal tails emerging over geological time, and understand they lived inside one of the universe's grand recurring processes. Their poets would be insufferably busy. Their scientists would be delighted. There is also the possibility that mergers help create future habitable worlds indirectly. Starbursts enrich galaxies with heavy elements forged in massive stars and supernovae. Those elements later become rocky planets, oceans, atmospheres, and chemistry. So, a galactic encounter may disturb some worlds while helping create ingredients for others not yet born. Destruction and creation often travel together in astronomy. Modern simulations track stars through mergers and estimate changing environments. They suggest that while some systems face perturbations, many stars simply continue onward on new galactic orbits. The drama is real, but it is statistical and structural more than universally apocalyptic. That distinction matters. Not every grand event is a disaster at every address. Lift your eyes, for a moment, from the ordinary version of the night sky. Imagine the familiar stars still present, the constellations still recognizable for now, the quiet path of the Milky Way still arching overhead. Then add something new, another entire galaxy growing larger year by year, age by age, until it no longer appears as a faint smudge in darkness, but as a second sky arriving. That is the heart of tonight's question. What would it look like if the Milky Way met another sky face to face? We already have a likely candidate. The Andromeda Galaxy, our nearest major galactic neighbour, is moving toward us and is expected to merge with the Milky Way in several billion years. It is presently visible from dark locations as a dim, elongated patch, though many city lights and tired schedules prevent the introduction. Yet if time were generous enough to let us watch the future unfold, Andromeda would become one of the most astonishing sights any civilization could inherit. At first, the change would be subtle, across human lifetimes, nearly imperceptible. Across thousands of years, careful astronomers might measure a slightly larger apparent size. Across hundreds of thousands or millions of years, it would become brighter, broader, and more detailed. A once faint mist would reveal structure. Its core would sharpen. Its disk would span increasing portions of the sky. Night after night, generation after generation, another galaxy would be approaching in plain view. It would be the slowest dramatic event imaginable. The current angular size of Andromeda is already larger than the full moon if one includes faint outer regions, though most of that extent is too dim for casual eyes. In a future closer approach, brightness and visible extent would increase greatly. Dark sky observers might see lanes, asymmetries, and star cloud texture. Children would grow up thinking galaxies in the sky were normal. History books would need footnotes explaining that earlier ages had less ambitious horizons. As the two systems drew nearer, the sky would stop feeling like a collection of distant points and begin feeling like structure. That word matters. Today, most stars appear as points because they are far and unresolved. A nearby approaching galaxy on grand scale would appear as shape, a glowing disk, bright nucleus, mottled regions, perhaps visible spiral patterning depending on dust, angle, and distance at each stage. The heavens would gain architecture. Even people uninterested in astronomy might become casually excellent at astronomy. There is another subtle shift worth noticing. Our sense of outside would change. At present, many people imagine space as remote, but if another galaxy visibly dominated the sky, the universe would feel less theoretical and more immediate. It is difficult to ignore a neighbouring star city larger than continents overhead. Now let us move to the first major close pass. Galactic mergers often do not happen as one clean head-on plunge. Instead, two galaxies swing past each other, distort, separate somewhat, then return. During that first close encounter, tidal forces would begin dramatically reshaping both galaxies. From our viewpoint inside the Milky Way, the sky could become extraordinary beyond simple description. Andromeda might stretch into luminous arcs. The Milky Way's own starband, already a river of light across our sky, could become warped and thickened in some directions. Tidal tails, vast streams of stars pulled outward by gravity, might appear as new bands or diffuse fans spanning the darkness. Imagine familiar constellations still there locally, but behind them the larger canvas itself is being repainted. That would be one of the strangest aspects. Local stars remain relatively nearby and still dominate the nearest visible pattern, while the deep background transforms around them. Constellations are neighbourhood art, galactic mergers are city planning. The stars closest to Earth would continue moving according to their own proper motions, though over immense times they shift too. But the grand luminous fields behind them would increasingly reflect the encounter. One could look up and see both intimacy and enormity at once. A bright nearby star, a changed constellation. Behind it, an entire tidal bridge between galaxies. Somewhere else, a glowing knot of merger-triggered star formation, and perhaps a philosopher needing to sit down. Would nights become much brighter? In many regions, somewhat brighter skies are possible depending on stage, orientation, and our location within the evolving system. A larger nearby galaxy full of unresolved stars adds diffuse light. However, it would not turn midnight into daylight. The brightness would be impressive, not blinding. Think more along the lines of majestic celestial presence than outdoor reading lamp. Though astronomers naturally would request both. As gas clouds collide and compress during merger phases, bursts of star formation could create bright clusters and nebula-like regions visible from afar. Massive young stars shine intensely. If enough formed in visible sectors, some portions of the sky might look richer and more textured than today. Certain nights under dark conditions could resemble a permanent celestial festival curated by gravity. Dust would complicate the view. Both galaxies contain dust lanes that absorb visible light. Some regions might darken dramatically, cutting great shadowed seams through bright stellar backgrounds. Infrared-sensitive beings, if any happen to be listening, would enjoy alternative scenery. The shape of the show also depends on where the solar system ends up. During a merger, stars are redistributed onto new orbits. Our Sun could be nudged into a more distant halo path, remain in an outer region, or shift into a new orbit within the merged remnant. Simulations suggest many possibilities. From one location, the final merged core might dominate the sky. From another, the central brilliance might be more modest, seen from afar. Address matters, even cosmically. Would Earth itself remain comfortable enough to watch? That depends less on Andromeda than on the Sun. Several billion years from now, solar evolution is expected to be a far more pressing issue for Earth's habitability than the galactic merger. The Sun will gradually brighten long before entering later red giant phases, so if one imagines actual observers watching the full event, they may be future descendants elsewhere in the solar system, migrated civilizations, unrelated life on other planets, or simply hypothetical patient stargazers with excellent planning. Still, the visual thought experiment remains delightful. Picture standing on a temperate moon around some future world. You step outside. Above you spans not one milky band, but multiple luminous rivers crossing the sky. One horizon glows with the warped remnant of Andromeda. Another carries a stream of stars torn from the old Milky Way disk. Over centuries, careful records show visible change. You live in a time when astronomy is not archival. It is current affairs. There may also be periods of enhanced meteor curiosity, cultural reinterpretations of ancient constellations, and widespread arguments over which balcony has the best view. Civilizations often meet grandeur with practical concerns. The final merged galaxy, sometimes informally nicknamed Milkomeda, would likely become more elliptical or spheroidal over time, with less distinct spiral structure than either original galaxy. The spectacular twin-disk phase would eventually settle into a smoother giant system. So the most dramatic sky would not last forever. It would evolve from approach to close pass to distortion to streaming tails to repeated encounters to final settling. Even the greatest sky show transitions through acts. There is something moving in that sequence. Two elegant spirals, each with their own long histories, gradually lose their separate identities and become a new shared structure. From within, the process would feel less like destruction, and more like endless rearrangement. Night after night, the heavens teaching that permanence was always a temporary convenience. Would people fear it? Likely some would. Would others celebrate it? Certainly. Would artists become unbearable with inspiration? Without question. Human cultures have always responded to the sky with stories, calendars, myths, mathematics, navigation, longing, and occasional confident misunderstandings. A merger sky would multiply all of that. Religions might reinterpret the event. Poets would compare love to tidal tales. Architects would overuse spiral motifs. Economists would somehow involve property values. Science, meanwhile, would flourish. With another galaxy so near and so active, observers could study star formation, stellar streams, dust lanes, variable nuclei, and galactic dynamics in exquisite detail. The universe would be performing its own textbook overhead. There is a gentler lesson hidden here too. We often think of the sky as background, fixed and passive, but the sky is process. It changes even now, only slowly enough that we call it still. A future face-to-face meeting with another galaxy would simply make that truth impossible to ignore. Nothing in a galaxy merger happens only once if gravity can arrange a second meeting. That may be one of the most surprising features of these encounters. Many people imagine two galaxies heading straight toward each other, colliding dramatically and immediately becoming one confused object. A single crash, one decisive moment. Credits roll. The universe is usually less hurried and more intricate than that. When galaxies approach, they often do not merge in one pass. Instead, they sweep near each other, distort each other, continue onward for a time, slow under mutual gravity, curve back again, and return for another encounter. Their meeting can resemble a prolonged dance of loops, arcs, and repeated close approaches spread across hundreds of millions or billions of years. It is less like two cars colliding and more like two ice skaters circling, grabbing sleeves, spinning apart, then gliding back together because physics insists. Let us begin with motion. Galaxies are rarely motionless before they meet. Each already travels through space with its own velocity, direction, and internal rotation. When two galaxies become gravitationally bound, they do not necessarily aim center to center. Usually there is sideways motion as well, what physicists call tangential velocity. That sideways component matters enormously. If two objects move directly toward one another with no sideways motion, a head-on plunge is possible, but give them lateral movement and they miss the exact center, curving into orbital paths around their shared center of mass. This is common throughout the cosmos. The Earth falls toward the Sun continuously, but sideways motion turns falling into orbit. The Moon does the same around Earth. Satellites orbit planets. Stars orbit galactic centers. With galaxies, the principle remains familiar while the scenery becomes outrageous. Two star cities each containing hundreds of billions of stars can begin orbiting one another on vast trajectories. During the first close pass, tidal forces grow strong. Spiral arms stretch. Tails of stars and gas are drawn outward. Bridges form between the galaxies. Gas flows inward toward central regions. To an observer, it may look like the merger is already complete. Yet often the galaxies continue past one another. Why do they not simply fly apart forever? Sometimes they can, if the encounter speed is high enough and the gravitational binding weak enough. But many interacting galaxies lose orbital energy during the pass. That energy is redistributed into internal motions of stars, gas turbulence, and especially through a process called dynamical friction. Dynamical friction is one of those terms that sounds mechanical while being entirely gravitational. As a galaxy moves through another galaxy's halo of stars and dark matter, it creates a trailing wake of enhanced density behind it. That wake exerts a gravitational pull backward, slowing the moving galaxy. No surfaces rub, no brakes squeal, yet energy is steadily drained from the orbit. So after the first pass, the galaxies may separate, but not as freely as before. They climb outward on a weakened trajectory, slow, and then begin falling back together. This creates the repeated pass structure seen in many simulations and inferred from many observed systems. Close approach, distortion, separation, return, closer approach, greater distortion, eventual union. It is choreography written by gravity and patience. If you could watch such an encounter with time accelerated, the galaxies might seem alive in a way still images never fully convey. They would stretch into crescents, sling tails behind them, rotate through each other's outskirts, then turn back like dancers unable to leave the floor. Their centers might remain distinct for long intervals, each carrying its own dense core and often its own supermassive black hole. two hearts, one growing future. The famous antennae galaxies likely represent a system in one of these intermediate stages. Their long tails suggest a previous close encounter, while the two galactic cores remain identifiable. They have not simply collided once and vanished into one shape. They are mid-story. Astronomy often catches galaxies between verbs. The paths involved are not neat circles. They are usually elongated, decaying orbits. Each pass changes the next one. Mass has been redistributed. Gas has moved. Tidal tails carry away angular momentum. Halos overlap more strongly. The geometry evolves. So the second encounter is not a replay of the first. It is a sequel with altered circumstances. Sometimes one galaxy may pass above or below the disk of another, depending on inclination. If the disks are tilted relative to the orbital plane, the visual structures can become especially dramatic. Warps, shells, rings, and offset streams may result. A slight change in angle at the beginning can produce entirely different final artwork. This is why astronomers run large suites of simulations with varying initial conditions. Adjust mass ratios, gas content, spin direction, orbital angle, or relative speed, and the merger changes character. The universe uses the same laws repeatedly while still avoiding repetition. There is also an important concept called angular momentum. Whenever objects orbit, angular momentum helps preserve rotational motion. To merge efficiently, galaxies must redistribute some of that momentum. Tidal tails and outer streams often help carry it away. Gas can lose angular momentum and sink inward. Stars may be scattered into more randomized orbits. The result is that the dance itself helps end the dance. By flinging some material outward and stirring the rest inward, the system creates conditions for eventual coalescence. Think of two figure skaters holding hands and spinning faster as they draw inward, while scarves fly off dramatically, carrying some momentum away. Physics would object to details, but not the spirit. Repeated passes can also trigger multiple waves of star formation. During one close encounter, gas clouds compress and produce a burst of new stars. During separation, activity may ease. On the next pass, fresh inflows and collisions can ignite another burst. So a merger can pulse with episodes of creation rather than one continuous blaze. This matters when astronomers reconstruct histories from stellar ages. A galaxy remnant may contain populations of stars born during different stages of the interaction. The stars themselves become timestamps. What would this look like from a planet inside one of the galaxies? For long ages, a companion galaxy would loom large, then drift partly away, then return even larger or more distorted. The sky would not simply brighten once and conclude, it would evolve through acts. A close pass might produce spectacular tidal arcs across the heavens. Later, the companion could recede somewhat while still stretched and luminous. Generations later, it would swing back into a more intimate arrangement. Entire mythologies could develop around the returning sky. Some cultures would call it a promise, others would call it a warning. Scientists would call it orbital decay and then try not to sound pleased. Meanwhile, local planetary life could remain relatively ordinary. Days still depend on rotation, weather still depends on atmosphere, meals still depend on planning. Cosmic grandeur rarely washes the dishes. There is comfort in that repeated contrast. Large motions overhead, small routines below. Repeated passes also help explain why many merger remnants eventually lose their clean spiral forms. Each encounter stirs stellar orbits, thickens disks, drives gas centrally, and erodes the ordered rotation that once defined spiral structure. By the final union, the original galaxies may be hard to recognize except through surviving streams and the memory written into star motions. Order has not vanished, it has changed categories. Sometimes a smaller companion experiences this even more dramatically. In a minor merger, a dwarf galaxy may loop repeatedly around a giant host, each pass stripping stars and gas until only streams remain. The dwarf's identity becomes elongated traces around the larger galaxy. Our own Milky Way contains such stellar streams from past meals and ongoing snacks. Galactic history can be read as leftovers in orbit. There is something elegant in the fact that gravity prefers curves over straight endings. We often think in terms of direct paths, approach, impact, finish. Yet many natural systems move through cycles, returns, and gradually tightening loops. Planets circle, comets revisit, moons tide lock, galaxies pass, return, and merge through repetition. Even learning often works this way. We revisit ideas, each pass a little deeper than the last. The cosmos seems fond of revision. Eventually, the repeated encounters shorten. Separation after each pass becomes smaller. Distinct cores draw nearer. Tails fade or fall back. Gas reservoirs are consumed, heated, or centralized. Central black holes begin their own slower inward spiral toward one another. The dance floor narrows. From a distance, some galactic mergers look as though the universe has been painting with long brushes. Two bright cores may sit near one another in tension, while from their edges extend sweeping ribbons of stars, gas, and dust reaching far into darkness. These structures can curve gracefully, fork, fade into mist, or stretch in opposite directions like luminous banners caught in a slow invisible wind. They're among the most beautiful features in astronomy. They're also evidence that gravity is exceptionally good at rearranging things without touching them directly. These structures are called tidal tails, stellar streams, bridges, shells, and plumes, depending on their form and origin. Tonight we'll stay with the broad image, tails of light. They appear when galaxies interact strongly enough that stars and gas are pulled from their older orbits and launched into new paths. To understand why, let us return to the key idea of differential gravity. When one galaxy passes near another, the side facing the companion feels a stronger pull than the far side. That difference stretches the galaxy. Inner regions remain more tightly bound, while outer material is easier to disturb. Stars near the outskirts can gain energy or have their orbits redirected. Gas clouds can be dragged along, compressed, or flung outward. The result is not random scattering. It is organized disruption. Material streams out along paths determined by orbital motion, galaxy rotation, encounter angle, and the distribution of mass, including dark matter halos. So these tails are not debris in the everyday sense. They are trajectories made visible. Imagine spinning while holding a handful of glitter, and then opening your hand at exactly the wrong moment. The glitter flies outward in elegant arcs shaped by your motion. Replace glitter with stars and millions of years, and you begin to approach the concept. One of the most famous examples is the antennae Galaxies. Their two long tails extend outward from the merging pair and give the system its name. Those tails likely formed during a close pass that pulled outer stars and gas into elongated streams. Another striking case is the mice Galaxies, whose narrow tails resemble long cosmic whiskers. Their shapes tell astronomers that a dramatic encounter is underway. Galaxies leave signatures of their motion written in stretched light. Tails can be enormous. Some extend hundreds of thousands of light years, larger than the visible diameter of many galaxies. That scale is difficult to hold in mind. A feature formed as a side effect of an encounter may become larger than the systems that created it. Astronomy enjoys overachieving. Why do outer regions provide so much of the tail material? Because stars in the outskirts of a galaxy are generally less tightly bound than stars deep near the centre. They orbit in shallower gravitational wells. A strong tidal pass can nudge them enough that their former circular orbits become elongated paths extending far from the disk. The central bulge often remains relatively intact at first. The edges become expressive. Gas in these tails behaves differently from stars. Because gas clouds can collide and cool, they may condense into knots. Some of those knots can form new stars. In certain cases, enough material gathers to create small, self-gravitating systems, known as tidal dwarf galaxies. That means a galaxy interaction can tear matter outward and then allow that same matter to assemble into new miniature galaxies. Even being flung away does not necessarily end the story. Dust accompanies the gas as well, dimming some regions and glowing in infrared wavelengths. Tails that seem faint in visible light may reveal richer structure under other instruments. Radio observations of hydrogen gas often show tails extending farther than starlight alone suggests. The visible stream may be only the headline, there is usually more in the fine print. The exact shape of a tail depends on geometry. If two spiral galaxies meet with disks aligned one way, broad symmetrical tails may form. Tilt the disks differently, and one tail may dominate while another becomes shorter or more diffuse. Increase relative speed, and the structures may be less pronounced. Change the mass ratio, and the smaller galaxy may be dramatically stripped while the larger one grows only modest tails. Tiny changes at the beginning can lead to wildly different cosmic calligraphy. This is why astronomers use simulations so heavily. By modelling millions of particles and varying initial conditions, they reproduce observed tails and infer the past motions of real systems. A tail is not just pretty, it is evidence. When scientists see a long stream curving from a galaxy, they can ask, which direction did the companion pass? How close was the encounter? How much mass did each galaxy have? How much dark matter is implied by the way the stream moves? Beauty and data are happily compatible. Not all streams come from major mergers. Smaller galaxies orbiting larger hosts can be tidally shredded over time, leaving stellar streams wrapped around the host like faint ribbons. The Milky Way itself contains such streams from past and ongoing encounters. One well-known example is the Sagittarius dwarf spheroidal galaxy, which is being torn apart by the Milky Way's gravity. Its stars are spread into streams looping around our galaxy. So while we speak of dramatic two-giant collisions, quieter versions happen regularly. Large galaxies often grow by slowly unweaving smaller neighbours. Space can be majestic and opportunistic at the same time. There are also shells, faint arc-like layers around some galaxies, especially ellipticals. These may form when a smaller galaxy falls in, and its stars pile up at turning points in their new orbits, creating ripple-like structures. To the eye, they can resemble the ghostly rings left by stones dropped in a pond. Even after the merger settles, the memory remains visible. That idea deserves a pause. Galaxies remember encounters through structure. A tail may persist for hundreds of millions of years before dispersing. A shell may linger as a faint signature. Streams can orbit for immense times. Long after the dramatic close pass, evidence remains written in stars. Humans also carry history in shapes and patterns, though usually with fewer hydrogen clouds involved. What would cosmic streams look like from within a merging galaxy? That depends on where you stand. If you lived on a planet orbiting a star in a relatively calm region, the night sky might gradually develop vast new arcs of unresolved starlight. A stream passing overhead could resemble an additional Milky Way-like band, thinner or more curved than the original. Another tail might rise seasonally like a second luminous river. Dark dust lanes could divide portions into shadowed seams. No telescope required for wonder. Yet the process would still be slow. Individual generations might see only modest changes. The full transformation would span timescales beyond ordinary memory. Civilizations would hand down sky maps showing streams thickening, shifting, fading, returning. Astronomy would become inheritance. Tails also help galaxies lose angular momentum. By carrying stars and gas outward, they remove some of the orbital spin budget of the interacting pair. This allows the central regions to sink closer and eventually merge more completely. So the tails are not just decoration, they are part of the mechanism. The galaxies create streams partly by giving away momentum to the outskirts. What leaves helps what remains come together. There is something elegant in that exchange. Sometimes union requires letting some things go. In gas-rich mergers, streams may also feed material back inward later. Some tail matter remains bound and can fall back toward the remnant galaxy, contributing to later star formation or rebuilding extended structures. Even escape may be temporary. Gravity is patient and often persuasive. Dark matter influences these tails too. A galaxy embedded in a more massive halo may hold onto material differently than one with a lighter halo. Tail length, thickness, and survival can provide clues about the unseen mass distribution. Again, what we cannot see shapes what we can. That is almost a recurring law of life as well as physics. There is another reason these structures fascinate us. They make motion visible. Space often looks static because timescales are too long, but tails are frozen gestures. They let us see that galaxies are not fixed islands, but evolving systems mid-action. A tail says, something happened here. A bridge says, something is happening. A shell says, something happened long ago. The sky becomes narrative. Eventually many tails disperse. Stars continue on separate orbits. The stream broadens and fades. New equilibrium emerges. But for a time, these luminous extensions transform galaxies into something theatrical. Not chaos exactly, more like gravity sketching with light. Deep inside many galaxies, far from the bright spiral arms and tidal tails that capture our attention, there is often a resident that prefers understatement. It does not glow by itself. It does not wave. It does not send postcards to the outer stars. Yet it can outweigh millions or billions of suns, shape the motion of nearby stars, and occasionally turn surrounding matter into one of the brightest phenomena in the universe. This is the supermassive black hole. As two galaxies begin their long merger, these central objects may start one of the most remarkable courtships in cosmic history. While stars are flung into tails and gas clouds ignite with new births, the hidden anchors at each galactic core slowly begin to notice one another. That phrase, notice one another, needs translation. Black holes do not possess awareness in the ordinary sense. They are regions of space-time where gravity becomes so strong that within a boundary called the event horizon, escape is no longer possible. They do not gaze across the dark and sigh thoughtfully about incoming company. But gravity notices everything, and when two galaxies merge, the gravitational centers that once ruled separate realms are gradually drawn into a shared future. Most large galaxies appear to host central supermassive black holes. Our own Milky Way contains Sagittarius A star, with a mass of roughly 4 million suns. The Andromeda Galaxy likely hosts an even more massive central black hole. Other galaxies contain giants far larger still. For long ages, each black hole sits at the dynamical heart of its own galaxy, surrounded by stars, gas, and dark matter moving in response to the total gravitational field. It is not the only source of gravity in the galaxy, but in the inner region it becomes especially influential. Then the galaxies begin to merge. At first, nothing dramatic happens between the black holes themselves because they remain far apart, often tens or hundreds of thousands of light years. That is an immense separation even for objects of great mass. But their host galaxies are being rearranged. Stellar distributions distort, gas flows inward, orbital energy is exchanged, and the galactic centers are no longer isolated. As the merger proceeds, each central black hole tends to remain associated with the dense core of its original galaxy. You can think of them as each carrying a compact entourage of stars through the larger interaction. Two royal courts moving through collapsing kingdoms. Eventually those cores approach each other. How do they lose enough motion to come together rather than simply pass and continue wandering apart? The answer, once again, involves dynamical friction. As each dense core moves through the background sea of stars and dark matter in the merging system, it gravitationally stirs a wake behind it. That wake pulls backward, draining orbital energy and momentum. Over time, the cores spiral inward toward the common center. The black holes are passengers inside this process at first. Their surrounding stellar nuclei do much of the braking. This stage can take a long time by human standards and a moderate time by galactic standards. Millions to hundreds of millions of years may pass while the two central regions close distance. Meanwhile, if enough gas is present, something visually spectacular may occur. Gas funneled toward galactic centers during mergers can feed one or both black holes. Matter spiraling inward forms an accretion disk, heating through friction and compression to enormous temperatures. The result can be an active galactic nucleus, quasar, or other luminous central engine. So paradoxically, black holes themselves emit no light, yet matter falling toward them can outshine whole galaxies. Two merging galaxies may therefore host dual-active nuclei, two bright central beacons in one disturbed system. Astronomers have observed several examples of galaxies with two active cores, interpreted as supermassive black holes still separated but sharing a merger environment. That means we can catch the process mid-story. One famous case is NGC 6240, where observations reveal two supermassive black holes in a merging galaxy. They are not yet one object, but two central engines in a common turbulent home. This is one of astronomy's recurring pleasures. The universe often leaves evidence visible long before the final act. As the black holes draw nearer, their relationship changes stages. At very large separation, each behaves mainly as the centre of its own core. At smaller separation, the pair becomes gravitationally bound to each other. Now they form a binary black hole system. That phrase may sound sudden and cinematic, but the reality is patient. Two supermassive black holes orbiting one another can still be separated by light years. Their dance is slow, massive, and governed by surrounding stars and gas. Stars passing near the binary can steal orbital energy and be flung outward on accelerated trajectories. Gas disks can torque the pair inward. The orbit gradually shrinks, the binary hardens. Astronomers actually use that term. A hard binary is one whose components are tightly bound and become tighter through interactions. It sounds severe, but the mathematics approves. There is an interesting challenge here known historically as the final parsec problem. A parsec is about 3.26 light years. In some simplified models, once two supermassive black holes get within roughly parsec scales, it was unclear whether enough stars or gas would remain available to keep extracting orbital energy efficiently. Would the pair stall? Would they orbit for ages without merging? Modern studies suggest triaxial galaxy shapes, fresh stellar supplies, gas dynamics, and other complexities often help the process continue. Nature appears less easily stalled than our first simplified equations feared. This is reassuring for both astronomy and anyone waiting on long paperwork. What would it look like nearby? If you were somehow observing from a safe distance within the host galaxy, the black holes themselves might remain invisible unless accreting matter, but their surrounding regions could glow fiercely. Jets might erupt if magnetic fields and accretion conditions align. Gas clouds could be heated and ionized. Stars in the central region would follow unusual rapid orbits. The core of the galaxy might become a place of intense radiation and complicated opinions. Fortunately, most inhabited planets, if any exist, would hopefully choose to live elsewhere. Our own solar system sits far from the Milky Way's centre, and that distance has practical charm. When the Milky Way eventually merges with Andromeda, their central black holes are expected to participate in this long inward progression. First, the galaxies overlap, then the cores sync. Later, a binary may form. Much later still, under favourable conditions, the pair may merge. By the time that final union occurs, countless stars will have shifted orbits, tails will have faded, and the merged galaxy may already look largely settled from afar. This teaches an important lesson. Some of the most consequential events happen late in the process, long after the visible drama most people would call the collision. Surface spectacle and deep dynamics run on different schedules. There is also feedback to consider. Accreting black holes can launch winds and jets that heat, or expel gas from central regions, reducing future star formation. So while galaxy mergers often trigger starbursts, central black hole activity may later help shut some of that activity down. Creation and suppression can arrive in the same event. The universe does not prefer single-theme storytelling. Another subtle point is that black holes are not vacuum cleaners, roaming galaxies swallowing stars indiscriminately. Their gravitational influence obeys the same distance laws as any mass. If the Sun were replaced by a black hole of equal mass, Earth would continue orbiting similarly, though with obvious lighting concerns. What makes supermassive black holes important in mergers is not magical sucking power, but immense mass concentrated in galactic centers and the energetic consequences of accretion. Precision matters. So does debunking. There is something quietly poetic about these central encounters. Two galaxies may lose their arms, tails may fade, stars may scatter into new distributions, yet hidden in the middle, two dark objects continue drawing closer, carrying the memory of former separate systems. At the core of the merger, the past remains doubled for a while. Eventually, of course, the binary itself becomes the main story. As the orbit tightens further, another phenomenon begins to matter more and more: gravitational waves, ripples in space-time carrying energy away from the pair. By the time two supermassive black holes begin their final inward spiral, the galaxies that once carried them may already look like old stories blended together. Spiral arms have been stretched, broken, or erased. Tidal tails may still linger as faint rivers of stars far from the center. Gas has surged inward, ignited bursts of star formation, perhaps fed bright active nuclei, then partly settled or been blown outward again. The two original galactic identities have become difficult to separate. Yet at the core, something remains unfinished. Two immense masses, each once ruler of a separate galaxy center, now orbit one another in darkness. This stage is one of the most extraordinary consequences of galactic mergers, the creation of a binary system made not of stars or planets, but of supermassive black holes. To picture it properly, scale must be handled with care. These are not small black holes zipping around dramatically every few minutes like cinematic props. Each may contain millions or billions of times the mass of the Sun. Their separation may still be measured in light years when the binary forms. Their orbital periods can span years, centuries, or longer depending on mass and distance. The dance is real. The pace is unbothered. At first, stars and gas around the pair continue helping remove orbital energy. Stars that pass near the binary can be flung outward at high speed, stealing some of the pair's energy in the process. Gas disks can exert torques. Irregularities in the merged galaxy's shape can keep sending fresh stars into useful encounters. The orbit gradually shrinks. Each revolution brings the black holes a little closer. This phase can last millions of years. Nothing about it feels rushed unless you're a geologist. Eventually, however, another mechanism becomes dominant, one predicted by Albert Einstein and confirmed by modern observation: gravitational waves. These are ripples in space-time produced by accelerating masses. When extremely massive objects orbit each other, especially compact ones like black holes, they disturb the geometry of space-time itself. Energy is carried away as waves moving outward at the speed of light. As energy leaves the system, the orbit tightens faster. The pair spirals inward. This is not friction in the ordinary sense. Nothing rubs. No medium is required. Instead, the binary loses energy through the changing curvature of space-time. It is a wonderfully elegant sentence for nature to write. Move enough mass in the right way, and space itself carries the news outward. Smaller black hole mergers, those involving stellar mass black holes, have already been directly detected through gravitational wave observatories such as LIGO and Virgo collaboration. These events produced fleeting distortions smaller than an atomic nucleus across kilometre-scale instruments. Supermassive black hole mergers are expected to generate waves of much longer wavelength and enormous power. requiring different detection methods such as pulsar timing arrays and future space observatories like LISA. So while we may not hear them with ears, astronomy is learning to listen with exquisite patience. Imagine two giants orbiting ever faster as the gap narrows. At large separations, the motion is stately. At smaller separations, the period shortens. Closer still, velocities rise dramatically. The final stages become a runaway, inward sweep. For stellar mass black holes, this last phase can happen in seconds. For supermassive binaries, the observable in spiral near the end may still represent an immense event, though the exact times depend strongly on mass and separation. Then comes merger. Two event horizons become one larger horizon. A newly combined black hole forms, carrying nearly all the mass of the pair minus the portion radiated away as gravitational waves. It settles from a disturbed state by emitting additional waves, a stage often called ring down. The name sounds gentle. The physics is not casual. For a brief period, the power released in gravitational waves can exceed the combined light output of all stars in the observable universe, though again, it is not ordinary light. It is energy in space-time waves. The universe occasionally becomes dramatic in channels our eyes cannot see. There is another fascinating possibility: recoil. If the merger is asymmetric enough because of differing masses or spin orientations, the emitted gravitational waves may carry momentum unevenly. Conservation of momentum then gives the newly merged black hole a kick. That kick can launch it through the host galaxy at hundreds or even thousands of kilometers per second in extreme cases. Picture the heaviest object in the galaxy being shoved by its own gravitational wave exhaust. Physics can be delightfully audacious. In modest recoil cases, the black hole may oscillate around the galactic center before settling back. In stronger cases, it might be displaced far from the core. In rare theoretical extremes, it could even escape smaller galaxies entirely. A galaxy losing its central black hole is not the most common administrative outcome, but the option exists. What would all this look like from a safe distance star system inside the merged galaxy? Probably less cinematic than films prefer, but still remarkable. You would not see two black holes as glowing spheres colliding. Black holes themselves remain dark unless matter around them shines. If gas is present, the central region might blaze as an active galactic nucleus. Jets may form, radiation may surge, variable light signals could emerge from disturbed accretion flows. But the most important action would be hidden in gravity. The central stars might move in unusual patterns. Gas clouds could be heated or expelled. The nucleus might brighten, flicker, or shift. To instruments, it would be extraordinary. To the unaided eye from far away, perhaps simply a very bright and peculiar galactic center. This reminds us again that reality often saves its best details for those who measure carefully. Our own future offers a version of this story. The Milky Way contains Sagittarius A star. The Andromeda Galaxy likely hosts a significantly larger central black hole. When those galaxies merge billions of years from now, their central black holes may eventually form a binary and later unite. By then, the Earth will face concerns much closer to home involving the Sun's evolution, so human attendance is uncertain. Still, the cosmos will proceed whether tickets are claimed or not. There is also a broader significance to these unions. Supermassive black hole mergers help build the largest black holes over cosmic time. Galaxies merge repeatedly across history, and their central black holes may grow through both accretion and mergers. Thus, some colossal black holes seen in giant galaxies today are likely archives of many past unions. Their mass is historical record. Every additional billion solar masses may represent ancient meals, steady feeding, and long-forgotten pairings in vanished galaxies. These mergers can also influence galaxy evolution. Energy released through accretion around the newly merged black hole may drive winds that heat gas or prevent future cooling, suppressing star formation in the host galaxy. So the central union may help determine whether the galaxy remains fertile with new stars, or grows quieter and redder over time. A private event in the nucleus can shape millions of light-years of future demographics. There is something strikingly human about that scale mismatch. Tiny centres, enormous consequences. We often think the most visible parts of systems matter most, yet galaxies repeatedly remind us that hidden cores can guide destinies. One more subtle point. Even when two black holes merge, nothing magical tears open space in the science fiction sense. No portal appears, no stars are vacuumed instantly inward. Gravity changes smoothly according to the new combined mass and emitted waves. Reality remains disciplined even at its grandest moments. That discipline is part of what makes it beautiful. As the merged black hole settles into singular central authority, the host galaxy continues evolving. Stellar streams disperse, gas cools or escapes, star formation may decline. A smoother giant remnant emerges from what were once two separate spirals. The central pair is gone, the consequences remain. While black holes spiral together in hidden centres and stars continue their patient orbits, another side of galactic mergers can become almost extravagantly visible. Light surges, gas collides, dust glows, radiation pours from crowded central regions. Whole galaxies that once looked calm can transform into some of the brightest objects in the cosmos. If the earlier stages of a merger feel like choreography, this stage can feel like fireworks, though fireworks measured in light years, powered by gravity, and scheduled over millions of years. The key difference is that stars mostly pass one another without touching, but gas does not enjoy such personal boundaries. Galaxies often contain immense clouds of hydrogen, helium, dust, and molecular material spread through their disks. In ordinary times, this gas rotates, cools, forms stars gradually, and participates in long internal cycles. During a merger, those ordered motions are disrupted. Clouds ram into clouds, streams cross, pressure rises, shockwaves form. A shockwave in space is not exactly like a sound wave in air. Space is too empty for ordinary sound to travel far in the way we experience it. Instead, shockwaves occur when gas is compressed rapidly, creating abrupt changes in density, temperature, and velocity. Matter piles up faster than local pressure can smoothly adjust. Think of traffic suddenly bunching on a motorway, except the cars are hydrogen atoms and the motorway is a galaxy. When giant gas streams from merging galaxies meet, the compression can heat the material enormously. Later, some regions cool and collapse, helping trigger intense star formation. Other regions remain hot, turbulent, and glowing across multiple wavelengths. So shockwaves are both destructive and creative. They can tear clouds apart and help build new stars. This dual nature appears often in astronomy. Violence and construction are frequent roommates. One dramatic result is the starburst galaxy. A starburst occurs when a galaxy forms stars at a much higher rate than usual. Instead of a modest trickle of newborn stars each year, the rate may surge many times higher. Massive young stars appear in clusters, flood surrounding space with ultraviolet radiation, and later explode as supernovae. The galaxy brightens not because old stars suddenly became ambitious, but because new stars arrived in great numbers. These newborn giants are especially luminous. Massive stars burn fuel rapidly and shine brilliantly blue-white. They do not last long by stellar standards, but while alive they dominate the light of their neighbourhoods. A merger can therefore make a galaxy look younger, brighter, and busier for a time. The antennae galaxies again provide a famous example, with many bright star-forming knots visible where gas has been compressed by the encounter. Yet visible light is only part of the celebration. Dust mixed with gas absorbs starlight, especially ultraviolet and visible radiation, then re-radiates that energy in infrared wavelengths. Some merging galaxies become so bright in infrared that they are classified as luminous infrared galaxies or ultraluminous infrared galaxies. To the human eye, parts may seem obscured, To an infrared telescope, they can look like cosmic furnaces. This is why astronomy insists on using more than one kind of light. A galaxy can appear modest in visible images while secretly blazing in wavelengths our eyes never evolved to appreciate. We have many talents. Infrared night vision was not one of them. Then there are active galactic nuclei. When mergers funnel gas towards central supermassive black holes, matter spirals inward through an accretion disk. Friction, compression, and magnetic effects heat this material to extraordinary temperatures. The resulting radiation can outshine the rest of the host galaxy. If conditions are right, the core may become a quasar or similarly energetic active nucleus. Jets of particles can erupt from near the black hole, extending far beyond the galaxy itself. Winds may blast outward, carrying energy into surrounding gas. So a merger can host two major light shows at once: widespread starbursts across the galaxy, and a blazing central engine at the core. That is efficient use of available drama. Radiation from these processes spans the electromagnetic spectrum. Radio waves trace synchrotron emission from energetic electrons spiraling in magnetic fields. Infrared reveals heated dust. Visible light shows stars and ionized gas. Ultraviolet highlights hot young stars and active regions. X-rays expose very energetic gas, compact objects, and accreting black holes. Gamma rays may arise in the most extreme environments. A single merger can become a multi-wavelength festival of physics. Astronomers studying such systems are rather spoiled. Shock waves also help stir turbulence. Gas that was once rotating in relatively ordered patterns becomes chaotic, with eddies, shears, compressed fronts, and expanding bubbles driven by stellar winds and supernovae. This turbulence changes how clouds fragment and collapse. It may trigger some star formation while preventing other regions from settling. Even within the fireworks, there is negotiation. The brightest periods do not last forever. Starbursts consume fuel rapidly. Massive stars live fast and die young. Supernova explosions and black hole-driven winds can blow gas outward or heat it enough to stop efficient cooling. Over time, the galaxy may exhaust or lose much of the raw material needed for continued intense star formation. What blazes brightest can also burn through resources fastest. Many giant elliptical galaxies may owe some of their present quietness to such past energetic eras. They likely experience mergers, bursts, feeding black holes, and feedback that helped shut later star formation down. Calm old giants may have had spectacular youth. There is another kind of shockwave worth noting, those from supernovae. During starburst phases, many massive stars form nearly together. Since massive stars live only millions of years, a wave of supernova explosions can follow relatively soon after the burst. Their expanding shock fronts enrich gas with heavy elements and stir the surrounding medium. Iron, oxygen, silicon, calcium, ingredients later used in planets, rocks, oceans, and perhaps life, are spread through the galaxy. So the fireworks are also chemistry. What looks like destruction becomes supply chain management for future worlds. Imagine observing such a merger from a safe planet far away in the same galaxy. The night sky might show brighter nebula regions, glowing central sectors, and unusual diffuse light where dust reflects or emits radiation. Some wavelengths invisible to eyes would be especially intense, so advanced instruments would reveal a universe in full performance. To local inhabitants, astronomy would become less about distant abstractions and more about active weather on a galactic scale. Though even then, someone would still forget where they left their telescope lens cap. Would these fireworks be dangerous? Potentially, depending on distance. Nearby supernovae, strong radiation from active galactic nuclei, or increased energetic particle environments can affect atmospheres and biology. But galaxies are vast. Many star systems remain far from the most intense regions. Distance remains the universe's preferred safety feature. This is one reason our position in the Milky Way is relatively comfortable. Not too close to the centre, not in the emptiest outskirts, but in a reasonably suburban stellar district. Good schools, moderate radiation, manageable commute around the galaxy. Shockwaves also leave structures astronomers can map. Shells of hot gas, expanding bubbles, emission line regions, and disturbed molecular clouds all help reconstruct what happened. Observing these features is like reading scorch marks after a celebration no one attended in person. Because cosmic timescales exceed documentary schedules, astronomers build stories from remnants. And the remnants are generous with clues. There is something emotionally satisfying about this stage of mergers. We often think brightness means simplicity. A light is on or off. But in astronomy, brightness can mean compression, turbulence, hidden dust, newborn stars, magnetic fields, feeding black holes, and cascading feedback all happening together. Luminosity can be complexity made visible. That applies beyond galaxies too. Sometimes the most radiant moments in any system are not peaceful equilibrium, but intense periods of transformation. At first glance, galaxies can seem like permanent designs. A spiral galaxy appears so orderly that it feels intentional. Bright central bulge, elegant arms, dust lanes curling outward, stars tracing calm rotation through a flat disk. An elliptical galaxy can look equally settled, smooth and rounded, like something finished long ago. We tend to see these shapes as categories, almost like species that simply exist as they are. But galaxy shapes are not fixed identities. They are phases, they are outcomes of motion, fuel, gravity and history. And after a major merger, shape can change dramatically. When two galaxies collide, especially two sizable spirals, the result is often not a bigger spiral with slightly more enthusiasm. Ordered disks can be disrupted, stellar orbits scrambled, gas redistributed, and the graceful architecture that took billions of years to build may dissolve into something entirely different. This is one of the deepest truths of cosmic structure. Form remembers process. To understand how galaxies change shape, begin with rotation. A spiral galaxy such as our Milky Way is supported partly by organised motion. Many of its stars orbit in roughly the same plane around the centre. This collective rotation helps maintain a flat disk. Spiral arms arise from density patterns, star formation, and orbital behaviour within that rotating structure. The disk exists because many stars share a broadly coordinated movement. Now imagine another large galaxy arriving with its own mass, rotation, and direction of travel. During the merger, gravitational forces pull stars onto new trajectories. Some are flung outward into tidal tails, some are driven inward, some gain more elongated or tilted orbits. The neat common plane begins to break down. Instead of many stars circling in one organised disk, more stars end up moving in a wider variety of directions. This matters enormously. A rotating disk stays flat because motion is coherent. A swarm with mixed directions becomes puffier, rounder and more three-dimensional. That is one reason major mergers between spirals are thought to create many elliptical galaxies. The disks are not merely combined, they are dynamically heated. Dynamical heating sounds as though astronomers place galaxies in an oven. In reality, it refers to increased random motion. Stars that once followed relatively orderly circular paths are scattered into more chaotic orbits. The system becomes thicker, less planar, and less obviously spiral. No flames required. As repeated passes continue, tidal distortions stretch the galaxies. Bars may form or strengthen in central regions. Gas loses angular momentum and falls inward. Starbursts ignite. Central black holes may feed. Meanwhile, the stellar populations are being stirred more and more thoroughly. By the time the merger settles, the old spiral arms may be gone, not hidden, gone as organised structures. What remains can be a smoother remnant where stars orbit in many directions rather than in one clean disk. This remnant often resembles an elliptical galaxy. Ellipticals come in many sizes, from modest dwarfs to giants such as Messier 87. many likely formed through repeated mergers over cosmic time, especially in dense environments where interactions are common. A giant elliptical may therefore be less a born round object and more a long historical archive of consumed spirals, swallowed dwarfs, and settled chaos. Calm surfaces can hide dramatic ancestry. Colour changes too. Spiral galaxies often contain gas-rich disks where new stars continue forming, giving parts of them a bluer appearance due to hot young stars. After mergers, gas may be rapidly consumed in starbursts, heated, expelled, or trapped in ways that reduce future star formation. Without many new blue stars arriving, the galaxy gradually reddens as older stellar populations dominate the light. So a merger can help transform a blue star-forming spiral into a redder, quieter, elliptical-like system. The shape changes, the colour changes, the pace of life changes. There is something almost seasonal about that, though the seasons last billions of years. Not every collision ends this way. Minor mergers, where a small galaxy falls into a much larger one, may disturb the larger galaxy without destroying its disk. The host may thicken slightly, grow its halo, develop streams, or trigger bursts of star formation while remaining recognizably spiral. Large galaxies can absorb smaller companions the way trees absorb weather, changed but still themselves. Our own Milky Way has likely experienced many such minor mergers. Stellar streams and halo populations preserve evidence of past companions that were stretched apart and incorporated. The galaxy we call home is already partly assembled from earlier encounters. Nature prefers recycling over pristine originality. There are also lenticular galaxies, sometimes called S0 galaxies, which sit between spirals and ellipticals in appearance. They possess disks but little obvious spiral structure and often reduced gas supplies. Some may form when spirals lose gas through mergers or environmental stripping, leaving a faded disk without active arms. Imagine a spiral that retired from visible ornamentation. Environment matters greatly. In galaxy clusters, interactions can be frequent. Hot intra-cluster gas can strip cold gas from galaxies moving through it. Repeated gravitational encounters can disturb disks. Mergers and harassment reshape populations over time. As a result, dense clusters often contain many ellipticals and lenticulars, while more isolated regions may preserve more spirals. Where a galaxy lives helps determine what shape it can keep. There is also the role of gas fraction. In earlier cosmic eras, galaxies often contained more gas. Gas-rich mergers can be messy, luminous, and capable of rebuilding disks under some conditions after the main event. If enough gas settles back into rotation, a new disk may form around an older disturbed core. So not every merger permanently erases disk structure. Sometimes galaxies reinvent themselves. The universe is surprisingly open to second drafts. Computer simulations show this beautifully. Two spiral disks approach. They distort into tails and bridges. Their centers loop and return. Finally, the stars settle into a rounder remnant, while gas may centralize or later reform components depending on conditions. Watching such simulations is a reminder that shape in astronomy is a moving target paused for our convenience. What would this feel like from inside the galaxy? Probably less dramatic than from afar. A planet orbiting an ordinary star would still experience local gravity dominated by its host star. Seasons, days, and weather depend mostly on local factors, yet the night sky over immense timescales could change profoundly. The familiar bright band of the galaxy might thicken, twist, or split. A companion galaxy could fill the sky, then distort into arcs. Later, the final galaxy might lose the clear flat Milky Way band altogether, replaced by a broader, more diffuse glow of stars surrounding the sky differently. Future sky watchers might inherit no obvious spiral river overhead, but a rounder stellar haze with denser central brilliance. The heavens themselves would reveal that the host galaxy changed class. That would be a remarkable cultural moment. Constellations rewritten not by nearby stars alone, but by galactic identity. There is a deeper lesson here about categories. Humans like labels: spiral, elliptical, irregular. Labels help us think, but nature treats them as temporary descriptions of systems in motion. A child sees a caterpillar, a chrysalis, a butterfly, and may call them different things. Biology calls them stages of one process. Galaxies are not identical to insects, though the wings would be challenging. Still, the principle holds. Shape is often history made visible. Even after a merger settles, traces of earlier forms may remain. Faint shells, streams, kinematically distinct cores, unusual star populations and hidden rotation can betray past collisions. Astronomers use spectroscopy and deep imaging to uncover these clues. A galaxy may look serene while carrying signatures of old turbulence. Again, calm does not equal simple. The future Milky Way-Andromeda merger is expected to produce some kind of large remnant often nicknamed Milkomeda. Simulations commonly suggest a more elliptical-like system than either original spiral, though details depend on gas, timing, and orbital geometry. The night sky of that era would belong to a different home than ours. The solar system, if still relevant in any inhabited sense, would orbit within a galaxy whose ancestors once displayed grand spiral arms, now dissolved into memory. There is something moving in that thought. Structures we assume permanent are temporary arrangements with excellent public relations, yet loss of old form is not failure, it is transformation into another stable mode. Spirals are not superior to ellipticals, they are different chapters in galactic evolution. One turns with clear arms, one glows with distributed age. Each is beautiful in its own language. After all the fireworks and distortions end, does the merged galaxy ever truly calm down, or does motion continue beneath the smooth surface? Once a spiral galaxy has lost its arms, the transformation can feel almost personal. We become attached to spirals very quickly. Perhaps it is because they look familiar to us, ordered, rotating, patterned, elegant in a way that seems easy to admire. Their bright lanes curve outward with the confidence of something that knows exactly how to be seen. They appear active, youthful, and composed all at once. Then a merger arrives, and over vast stretches of time that graceful structure can be dismantled. What emerges afterward may be larger, rounder, smoother, and in some ways quieter. This is the path from spiral to giant elliptical world. To appreciate the change, it helps to understand what a spiral galaxy really is beneath the photograph. A spiral is not simply a picture of arms painted onto the sky. It is a rotating stellar disk supported by organized motion. Billions of stars orbit in a common flattened plane. Gas and dust circulate through that disk. Spiral arms arise from density patterns, star formation, and the traffic flow of matter moving through gravitational structures. The visible elegance depends on internal order. When that order is disrupted repeatedly, the appearance cannot remain the same. During a major merger, two galaxies pass near each other multiple times. Tidal forces stretch their outskirts into tails. Gas flows inward. Stellar orbits are altered. Some stars are flung far outward. Others sink toward the centre statistically as energy is redistributed. Most importantly, many stars stop moving in the tidy shared pattern that once maintained the disk. Instead of circling mostly one way in one plane, stars begin following a wider range of paths, tilted, elongated, crossing, randomized. As this happens, the flat disk puffs up. The spiral arms dissolve. The old visual identity fades. What remains is a more spheroidal system, supported less by organized rotation and more by the combined random motions of its stars. That is the essence of an elliptical galaxy, not a spiral that became blurry, a fundamentally restructured stellar society. Elliptical galaxies come in many sizes, but the giant examples are among the most impressive objects in the universe. They can contain trillions of stars, sprawling halos, hot gas atmospheres, and central black holes of extraordinary mass. One famous example is Messier 87, a massive galaxy at the centre of the Virgo cluster. It hosts a supermassive black hole whose image became historically important through the Event Horizon telescope. M87 does not display dramatic spiral arms. It does not need to. Its grandeur comes from scale, density, and history. Many giant ellipticals are thought to have formed through repeated mergers over billions of years. A spiral meets a spiral. Later the remnant absorbs dwarfs. Later still another substantial galaxy arrives. Layer by layer, the system grows. The result is less like a pristine design and more like a city built from centuries of additions. Every merger leaves stars. Every encounter alters motion. Every absorbed companion adds memory. This is why giant ellipticals often dominate galaxy clusters. In dense environments, mergers and interactions are common. A central galaxy may gradually accumulate surrounding members, becoming the heavyweight resident of the cluster. Space, like economics, often rewards scale once scale becomes established. There is also a striking change in stellar population. Spiral galaxies usually contain cold gas and active star-forming regions. New blue stars continue appearing in their disks. Ellipticals often contain older, redder stars, and relatively little cold gas available for fresh star formation. How does that happen? Mergers can trigger starbursts that rapidly consume available gas. Central black hole activity may heat or expel gas. Cluster environments can strip additional supplies. Over time, the easy fuel for new stars diminishes. The galaxy becomes older in visible character. Its brightest young blue populations fade. Longer-lived redder stars dominate the light. So the path from spiral to elliptical is not only a shape change, it is a change in tempo. A spiral often feels busy, an elliptical often feels settled. That impression can be misleading, of course. Stars still orbit. Dark matter still shapes motion. Hot gas still moves. Black holes may still feed occasionally. But compared with star-forming disks, giant ellipticals often project calm built from old turbulence. There is something profound in that. What appears smooth may be the result of many collisions averaged together. We see similar effects elsewhere in nature. A rough stone in a river becomes polished through countless impacts. A weathered landscape becomes gentle through repeated extremes. A galaxy can become serene-looking through a violent past. Astronomy repeatedly warns us not to confuse appearance with biography. Now imagine the future merger of the Milky Way and the Andromeda Galaxy. Both are large spirals today. Each has rotating disks, spiral structure, gas, and central black holes. When they merge over billions of years, simulations often suggest the final remnant may resemble an elliptical or lenticular giant more than either original spiral. The familiar Milky Way band across the sky could eventually disappear as a clean disk feature. Instead, future observers might live inside a broader, more rounded stellar system. No sweeping spiral river overhead. A different architecture of night. The local stars nearest any planet would still dominate much of the visible sky, but the overall galactic backdrop could feel less like a thin luminous lane and more like a fuller surrounding haze with a bright central concentration. Home would still be home. But home's shape would have changed. This raises an interesting point about identity. If the stars remain, if many planets remain, if matter is largely conserved, what exactly has been lost when a spiral becomes an elliptical? Mostly arrangement, and arrangement matters. The same ingredients can produce entirely different experiences depending on structure. A library, a landfill, and a cathedral may all contain stone, wood, and air. Form creates meaning. Galaxies teach the same lesson at enormous scale. Ellipticals are not failed spirals. They are rearranged spirals, accumulated histories, merger archives, and often cluster monarchs. Some giant ellipticals are surrounded by faint shells and streams, leftover traces of past mergers still visible in deep imaging. Others contain globular cluster systems numbering in the thousands, likely gathered from many absorbed companions. Their halos are museums, their centres are power seats, their smooth light hides crowded records. There's also the role of hot gas. Many giant ellipticals sit within extensive halos of X-ray, emitting gas heated to millions of degrees. This gas can be difficult to cool efficiently, helping suppress future star formation. Active black hole feedback may reheat it further. Thus, the galaxy remains massive yet comparatively quiet in making new stars. A wealthy kingdom with low birth rates, one might say, though the analogy should not be pressed too hard. What would life be like on a planet inside such a galaxy? That depends overwhelmingly on the local star system, as always. Yet the broader environment might differ from a spiral disk. There may be fewer giant molecular clouds nearby, potentially fewer fresh star-forming regions in some zones, and a different night sky appearance. The sky could feel older, less crowded with bright blue nurseries, more dominated by mature stellar populations. Though one should be cautious assigning emotional ages to stars, they did not request the metaphor. There is another subtle beauty in ellipticals. They reveal the cumulative nature of the universe. Not everything remains youthful and structured forever. Some systems pass into broader, slower states where memory is distributed rather than obvious. Spiral arms are statements, ellipticals are summaries. Yet summaries can be magnificent. One can also ask whether ellipticals stay elliptical permanently. Not exactly. They continue interacting, accreting, evolving, and occasionally reigniting limited star formation if new gas arrives. Nothing in astronomy is ever fully final. Even settled giants remain in process. That thought is oddly comforting. Completion is often just a slower phase of change. When we admire spiral galaxies, we admire visible order in motion. When we admire giant ellipticals, we admire what survives after order has been transformed many times. Both are forms of endurance. Somewhere inside every merging galaxy, if life exists at all, it is probably busy with very ordinary concerns. A creature may be finding food, a city may be arguing about taxes, someone may be trying to sleep while a neighbour experiments with music at unfortunate volume. An ocean may be turning beneath a quiet moon. Meanwhile, outside that local world, billions of stars are shifting through a cosmic reorganization lasting longer than most species could imagine. This contrast is essential. When we ask what happens to life inside a merging galaxy, we are really asking how grand-scale change translates, or often fails to translate, into local experience. The answer is nuanced, which is usually science's polite way of saying, it depends. Let us begin with the reassuring part. Most life, if it exists on planets orbiting ordinary stars, would not experience a galactic merger as an immediate apocalypse. Galaxies are vast. Stars are separated by tremendous distances. Even during collisions, direct star-star impacts are exceedingly rare. Planetary systems often remain bound to their host stars. So if you lived on a stable planet around a stable star in a relatively quiet region, your sunrise would still depend on planetary rotation, not on the merger schedule. Rain would still answer to atmosphere. Seasons would still depend on orbit and tilt. Daily life can continue beneath enormous cosmic events. This is one of the universe's gentler truths. Scale protects. Because galaxies are so spread out, much of the merger's drama occurs in structure rather than in constant local catastrophe. Stars shift onto new galactic orbits. Gas clouds collide and ignite starbursts elsewhere. Tidal tails form far overhead. But many planets continue circling their suns. That said, life does not inhabit galaxies uniformly. Location matters enormously. A biosphere near the calm outskirts of a galaxy may face very different conditions from one near a dense star-forming region or close to an active galactic nucleus. So let us tour the possibilities. First, the quiet suburban scenario. Our own Sun resides in a relatively moderate region of the Milky Way, not near the crowded centre, not in the emptiest halo. Such zones may offer advantages: fewer disruptive close stellar encounters than dense cores, lower radiation than central active regions, and enough heavy elements from past generations of stars to build rocky planets. If a merging galaxy contains similar regions, life there might notice the merger mainly through the changing night sky. A companion galaxy grows larger, new luminous streams appear, starfields subtly rearrange over ages, the heavens become extraordinary, while ecosystems continue mostly local business. Astronomy would become everyone's hobby, whether requested or not. Second, the crowded inner galaxy scenario. Near galactic centres, stars can be packed more densely. Encounters between stars are still not common in a human sense, but close gravitational flybys become more plausible over long timescales. Such flybys can perturb distant comet reservoirs or outer planets. Central supermassive black holes may also become active during mergers, flooding nearby regions with energetic radiation. Life too close to such centres may face a harsher environment. Not impossible, but more eventful. One might politely call it a vibrant neighbourhood. Third, the starburst region scenario. Mergers often compress gas and trigger bursts of new star formation. Massive young stars are bright, hot, and short-lived. They emit strong ultraviolet radiation and later explode as supernovae. A planetary system embedded near these regions could experience increased radiation hazards, changing atmospheric chemistry, or elevated supernova risk over millions of years. Yet star-forming regions also create new planets, so a merger can threaten some existing biospheres while laying foundations for future ones. Creation and risk arrive together often in astronomy. Fourth, the displaced traveller scenario. During mergers, stars may be scattered onto new galactic orbits. A star system once in a calm region might migrate inward, outward, or onto a more elliptical path through changing environments. The local star still dominates planetary gravity, but the wider neighbourhood changes. Imagine keeping your house exactly intact while the city around it slowly relocates. That is roughly the feeling. Could planets be ejected entirely? Yes, in some cases. Gravitational disturbances can destabilize systems and produce rogue planets, worlds no longer bound to stars. This does not require a merger, but mergers may increase opportunities through altered stellar encounters. A rogue planet would drift through darkness, perhaps retaining internal heat, subsurface oceans, or thick atmospheres under certain conditions, bleak to some, mysteriously cozy to others. Life there, if any, would redefine what sunlight means. Now let us consider intelligent civilizations. How would a technologically capable species interpret a galactic merger? They might detect it long before dramatic visible changes. Astronomers could measure the incoming galaxy's motion, model future passes, and understand the process as a normal stage of cosmic evolution. This knowledge matters psychologically. A society that understands slow, natural processes may respond differently than one interpreting sky changes through fear or myth alone. Then again, even informed societies can panic about ordinary weather, so predictions remain difficult. Still, a merger sky would be astonishing. An approaching galaxy expanding over millennia, bridges and tails visible across ages, bright new star-forming regions, perhaps dual-active nuclei in the far future. Cultural consequences would be immense. Religions might reinterpret the heavens, art would flourish, real estate brochures would become dramatic. There is also a practical side. Advanced civilizations might use the merger as an observational gift. Nearby interacting galaxies provide unparalleled chances to study star formation, black holes, dark matter distributions, and stellar dynamics. What for nature is process, for scientists is data. A merger could be the greatest research grant ever delivered overhead. Would life be more likely after mergers because of fresh star formation? Possibly in some eras. New stars mean new planetary systems. Heavy elements from supernovae enrich gas, aiding rocky planet formation. Yet many merger-triggered stars may form in turbulent environments less ideal for long-term stability. So the merger may create opportunities while also generating noise. The universe rarely optimizes for convenience. There is another timescale issue. Life requires time, often a great deal of it. Complex evolution on Earth took billions of years. If mergers repeatedly disturb certain environments too often, some regions may be less favourable for long uninterrupted biological development. More tranquil zones might offer better odds. This suggests that not all parts of galaxies are equally hospitable over cosmic history. Astrobiology increasingly cares about galactic ecology, not only planets. Where you orbit matters. When you form matters. What your neighbourhood has been through matters. Our own Milky Way has experienced past mergers with smaller galaxies, and is still here producing stars, planets, and one species curious enough to ask these questions. So mergers are not automatically sterilising disasters. They are part of how galaxies grow. Indeed, some of the atoms in our bodies may trace back to stars born or disrupted through ancient interactions long before the solar system existed. We are products of previous cosmic commotion. That is a quietly intimate fact. Suppose humans, or descendants of humans, still existed when the Milky Way meets the Andromeda Galaxy. The main challenge to Earth itself would likely be the Sun's evolution long before the merger fully unfolds. But if civilization spread elsewhere, future observers might witness the event from safer habitats in the outer solar system or beyond. They would see a sky no ancestor ever knew, Andromeda swelling across darkness, the Milky Way band warping, streams of stars forming, perhaps eventually a new merged galaxy surrounding them. Their daily concerns would remain familiar in many ways: food systems, engineering failures, relationships, taxes, presumably undefeated. This may be the most comforting lesson of all. Even amid galactic change, life tends to remain local. It experiences the universe through immediate scales first: family, shelter, weather, gravity, biology. The largest events filter downward slowly, indirectly, and unevenly. We often fear grand forces because they sound grand, but local resilience can be powerful. A forest grows while continents drift. A child laughs while stars explode elsewhere. A civilization may thrive while galaxies merge around it. None of this guarantees safety, of course. The universe offers no warranties, but it does offer perspective. Vast change does not automatically erase small meaning. Far above the immediate concerns of calendars, traffic, and locating the other sock, a future appointment has already been scheduled by gravity. No invitations were sent. No one asked if the timing was convenient. Yet the Milky Way and the Andromeda Galaxy are moving toward one another, and over billions of years they are expected to meet. This is perhaps the most famous future collision in astronomy, because it involves our own home galaxy. It turns an abstract cosmic process into a family matter. Let us begin with where Andromeda is now. The Andromeda Galaxy, also catalogued as M31, lies about 2.5 million light-years away. It is the nearest major spiral galaxy to the Milky Way, and one of the largest members of our local group, the modest gathering of galaxies that includes us, Triangulum Galaxy, and numerous dwarf companions. Under dark skies, Andromeda is visible to the naked eye as a faint, elongated patch. What your eyes detect is ancient light that began travelling toward Earth roughly when early human ancestors were walking the planet. So even tonight, Andromeda reaches us from deep time. Modern measurements show that Andromeda has a substantial radial motion toward the Milky Way. In simple terms, the distance between our galaxies is decreasing. The broader universe is expanding, yes, but local gravity can overcome expansion on smaller scales, where systems are gravitationally bound. That is why galaxy groups can merge even while the cosmos overall grows larger. The local neighbourhood has its own plans. Current models suggest a first major close approach in roughly 4 to 5 billion years, though exact estimates shift as measurements improve. After that, the galaxies are expected to pass, distort each other, separate somewhat, then return for further encounters before eventually merging more completely. So this is not a one-night event, it is a prolonged relationship. By the time the most dramatic phases occur, our Sun will also be much older. In fact, solar evolution is likely to matter more for Earth than Andromeda does. The Sun gradually brightens over time, and long before it becomes a red giant, Earth's climate and habitability are expected to be profoundly altered. This is a useful reminder. Sometimes the distant headline is less urgent than the local star. Still, if observers existed somewhere in the future solar system, or descendants of life had spread elsewhere, they might witness one of the grandest skies imaginable. At first, Andromeda would slowly grow larger over millions of years. What is now a faint smudge would become brighter, broader, and richly structured. Its core would intensify. Its disk might span a large region of the sky. Dust lanes and star clouds could become visible under dark conditions. Children of that era might assume every civilization gets a neighbouring galaxy overhead. Later comes the first close pass. Galactic mergers often begin with a sweeping encounter rather than an immediate fusion. The Milky Way and Andromeda may distort each other through tidal forces, drawing out streams of stars and gas. Spiral arms could stretch into long tails, bridges of material may form, gas clouds may collide and trigger starbursts. The night sky from a suitable world could become extraordinary. The familiar Milky Way band might warp or thicken. Andromeda could appear elongated, twisted, or split into luminous arcs. New rivers of starlight might cross the darkness where no ancient culture ever mapped them. Astronomy textbooks would need frequent updates. What happens to the solar system itself? Most likely the solar system remains bound to the Sun. Direct stellar collisions are extremely unlikely because stars are so widely separated. The Sun may be scattered onto a new orbit within the merged remnant galaxy, perhaps farther out than today, or onto a more elliptical path. Our address changes. Our house probably stays attached to its foundation. That said, by then the Sun's own aging dominates practical concerns. If Earth still exists in familiar form, it would already face severe solar brightening issues long before the merger completes. Future observers are therefore more likely to be hypothetical descendants living elsewhere, perhaps around outer system habitats or other stars entirely. The cosmos remains observable whether or not Earth keeps comfortable seating. Another participant complicates the story, the Triangulum galaxy. Triangulum is smaller than both the Milky Way and Andromeda, but still significant. Some models suggest it may interact with the future merge system, or participate earlier depending on orbital details. Real galaxy groups are rarely neat two-character plays. There are always supporting cast members. As the merger progresses through repeated passes, gas can funnel toward galactic centers. This may trigger active galactic nuclei if central black holes feed efficiently. Star formation may surge in waves. Over longer times, gas supplies diminish, and the final remnant may settle into a more elliptical or lenticular giant, sometimes informally nicknamed Milkomeda. The name sounds playful for an event lasting billions of years, yet it captures a real idea. Two identities blending into one new structure. Would the merged galaxy still contain the stars of both originals? Yes, overwhelmingly so. The stars are not annihilated, they are redistributed. Old populations mix. New stars formed during the encounter join them. Streams and halos preserve traces of origin for long ages. Galactic mergers are less about destruction of matter than rearrangement of trajectories. That distinction matters. We often fear change as loss, but much of cosmic change is recomposition. What would the sky look like after final merger? Instead of a thin spiral band like today's Milky Way, observers might see a broader, more diffuse stellar glow with a bright central concentration, depending on their location. Distinct spiral structure could fade. The galaxy may feel rounder, older, and more enveloping. Home would still be among stars, just under new management. There is also a scientific treasure in this future encounter. It helps astronomers test theories now. By measuring Andromeda's motion, mapping the Milky Way's mass, and simulating many orbital possibilities, scientists refine models of dark matter halos, galactic dynamics, and merger physics. The future event becomes a laboratory in advance. We cannot wait billions of years for results, so we compute them with admirable impatience. Emotionally, people often react to the Milky Way-Andromeda merger in two opposite ways. Some hear collision and imagine catastrophe. Others hear billions of years and lose interest immediately. Both reactions miss the richer truth. This event is not an imminent disaster, nor a boring distant abstraction. It is a window into how galaxies grow, how structures evolve, and how even our seemingly stable home is part of a moving universe. The night sky is not fixed, it is simply slow. That may be one of astronomy's most beautiful lessons. Stability often means change unfolding at a pace kind enough to feel still. Even now, Andromeda approaches, not dramatically enough to notice by eye tonight, but measurably enough for science to know the future arc of the story. Every second the gap closes a little. No rush, no malice, just gravity continuing a conversation begun long ago. Stand outside for a moment in imagination and look up from a future Earth. Not tomorrow's Earth, not next century's Earth. A far older Earth beneath a sky transformed by motion so slow that countless generations would have lived and vanished while the view changed almost imperceptibly year to year. Above you, the familiar night would no longer be familiar. This is the question many people quietly carry after hearing about the future meeting between the Milky Way and the Andromeda Galaxy. What might Earth's sky actually look like then? Before we begin, one practical note deserves honesty. Billions of years from now, Earth itself faces challenges unrelated to Andromeda. The sun gradually brightens as it ages. Long before its red giant phase, increasing solar luminosity is expected to alter Earth's climate severely. So a literal future human observer standing comfortably on present-day Earth is uncertain at best. Still, thought experiments are welcome guests in astronomy. Whether the observer is a distant descendant, an automated telescope, a visitor on an engineered world, or simply our present imagination, the sky remains worth exploring. Let us start early in the timeline. Today Andromeda appears as a faint elongated patch under dark skies. Many people never notice it because city lights compete aggressively with wonder. Yet over millions of years, Andromeda would slowly grow larger and brighter as it approaches. At first the change would be subtle enough that no single lifetime would notice it unaided. Careful astronomers comparing records across centuries might detect a measurable increase in size or brightness. Later civilizations comparing millennia of maps would see the trend clearly. The incoming galaxy would become a historical fact written in the sky. Eventually Andromeda would no longer be a dim smudge. It could appear broad enough that structure becomes visible, a brighter core, extended disk, perhaps mottled star cloud regions and dark dust lanes under excellent conditions. Imagine the full moon in apparent size. Then imagine something much larger in extent but softer and more diffuse, spanning a generous portion of the sky. People would plan vacations around dark nights just to stare upward. As the approach continues, the sense of distance would change psychologically. At present, galaxies feel remote because they appear faint and abstract. A bright neighbouring spiral dominating the heavens would make the universe feel nearby. Space would stop seeming like background scenery and start seeming like architecture. Now let us move closer to the first major pass. Galactic mergers often involve sweeping encounters rather than immediate fusion. During such phases, tidal forces distort both galaxies. Spiral arms stretch, streams of stars arc outward, gas clouds compress into star-forming regions. From Earth, or any surviving future equivalent world, the sky could become extraordinary. Andromeda might no longer look like a neat oval. It could elongate into sweeping luminous curves. One side may appear brighter than another. Long tails might extend across darkness like pale rivers. Meanwhile, our own Milky Way band could also change. The familiar lane of stars crossing the sky might warp, thicken, split in some directions, or merge visually with incoming structures. Imagine constellations in the foreground still recognizable locally, while behind them the grand background itself is being rewritten. That contrast would be remarkable. Nearby stars define the traditional constellations. They are local patterns within a relatively small stellar neighborhood. The galaxies are the wider cityscape beyond them, so even while the larger sky transforms, familiar bright stars might remain much where expected over shorter spans. You could still find old constellations. They would simply be standing in front of something astonishing. Would the night become bright enough to cast shadows? Probably not in a daylight sense, but some stages might noticeably enrich the darkness with diffuse glow. A large nearby galaxy full of unresolved stars can add gentle luminance. Under very dark conditions, nights may feel richer, more textured, less empty. Think more majestic twilight accents than outdoor newspaper reading. Though newspapers by then may have become more adaptable, dust lanes would add drama. Both galaxies contain interstellar dust that blocks visible light. Vast dark seams could cut through glowing backgrounds, creating high contrast patterns across sections of the sky. It would look as if the heavens had both painted and erased themselves simultaneously. Then there are starbursts. As gas collides during merger phases, new stars may form in great numbers. Massive young stars and bright clusters could create enhanced luminous patches in some regions. Nebula-like glows might become prominent. Certain sectors of the sky may appear richer with blue-white concentrations than anything familiar today. The universe occasionally redecorates with enthusiasm. Would there be danger from simply seeing this? No. Looking at galaxies, even very bright ones, is not harmful in itself. The real hazards from mergers would depend on distance from energetic events such as nearby supernovae or strong active galactic nuclei. But the visual spectacle alone would mostly be a privilege. Astronomy is often safer than social media. Another variable is the solar system's future galactic position. During the merger, the Sun may be nudged onto a new orbit within the eventual remnant galaxy. Simulations suggest the solar system could end up farther out, remain in an outer region, or follow a different path than today. Where we end up changes the view. From one location, the merged core might blaze prominently. From another, it might appear distant and centralized. From yet another, streams and shells could dominate while the center sits elsewhere in the sky. Real estate remains decisive. There is also the possibility that Earth, if no longer habitable at the surface, might still be observed by machines. Imagine robotic observatories on cooled lunar craters, outer solar system habitats, or orbiting platforms quietly documenting the changing heavens for millions of years. They would compile the longest time-lapse in history. No complaints, no coffee breaks. What would culture do with such a sky? Everything. Stories would multiply. Calendars might incorporate the shape of Andromeda's changing rise. Architecture could mirror tidal arcs. Music would claim inspiration from stellar streams. Someone would inevitably sell expensive property based on galaxy-facing views. Civilizations have always responded to the sky not merely with science, but with identity. A merger sky would become part of language itself. There is another emotional layer to this thought experiment. We often assume the sky above our ancestors resembles the sky above us and will resemble the sky above our descendants. But the heavens are not static inheritance. They are changing inheritance. The stars move. Galaxies move. We simply live during a calm-looking interval. Future skies remind us that permanence is often just slowness, mistaken for certainty. Eventually, after repeated passes and long settling, the Milky Way and Andromeda may merge into a larger, smoother remnant, sometimes nicknamed Milkomeda. Distinct spiral forms could fade. The dramatic two-galaxy phase would pass. Then the sky changes again. Instead of one clean Milky Way band and one neighbouring spiral, observers might see a broader diffuse stellar glow, perhaps more rounded, with a bright central concentration depending on location. Less theatrical contrast, more enveloping presence. Even endings in astronomy tend to become new middles. Would people miss the old sky? Almost certainly. Every generation mistakes its sky for the natural one. But future beings raised beneath a merger sky would feel differently. To them, twin rivers of stars or a giant approaching galaxy would be normal childhood scenery. Wonder adapts quickly. That may be the most human part of all this. We are fortunate to live in a universe that leaves the lights on during important events. Galaxy mergers take far too long for a human observer to watch one complete encounter from beginning to end. A single collision can unfold across hundreds of millions or billions of years. Even the most patient astronomer eventually needs lunch. So how do scientists study something so slow? They watch many different galaxies at many different stages. Some pairs are only beginning to approach, others are in their first close pass. Some display long tidal tails and active star formation. Others already share a common envelope with two bright nuclei still visible inside. Still others appear mostly settled, carrying faint shells and streams as evidence of old mergers. Put together, these systems form a kind of cosmic documentary assembled from scenes filmed in different places. No single galaxy performs the entire story for us. The universe offers examples instead. This is one of astronomy's great methods. When timescales are too long, compare many snapshots. Let us begin with what telescopes actually see. In visible light, interacting galaxies can look spectacular. Spiral arms become distorted. Bridges of stars connect companions. Tidal tails stretch outward into darkness. Dust lanes twist through bright regions. Double cores may appear where two galactic centres have not yet fully merged. The antennae galaxies are among the most famous examples. Their long tails and bright star-forming knots make them a classic laboratory for merger physics. Another striking pair is the mice galaxies, whose elongated tails suggest a dramatic close encounter. These are not rare curiosities. They are representative chapters. Visible light, however, tells only part of the story. Astronomers study collisions across the electromagnetic spectrum because different wavelengths reveal different ingredients. Radio telescopes trace cold hydrogen gas extending far beyond stellar disks. This gas often shows tidal distortions before visible stars do. Streams invisible to the eye can appear clearly in radio maps, showing that an interaction has begun even when photographs still look relatively calm. Infrared observations reveal warm dust heated by young stars or active galactic nuclei. Some mergers that appear modest in visible light blaze intensely in infrared because dust hides furious starbursts inside. Ultraviolet observations highlight hot young stars formed in compressed gas regions. X-rays expose hot gas shocked by collisions, energetic stellar remnants, and feeding supermassive black holes. Each wavelength adds a missing paragraph. Together they turn a pretty image into a physical explanation. Space telescopes have been especially valuable because Earth's atmosphere blocks or distorts parts of the spectrum. The Hubble Space Telescope provided exquisite images of interacting galaxies for decades, revealing star clusters, dust lanes, and tidal structures in remarkable detail. The James Webb Space Telescope now adds powerful infrared capability, peering through dust and exposing hidden star-forming regions and central activity that visible light cannot easily show. Meanwhile, observatories such as Chandra X-ray Observatory examine hot energetic gas, and radio arrays map hydrogen and molecular material. Astronomy succeeds partly because it refuses to use only one pair of glasses. How do astronomers know two galaxies are truly interacting rather than merely lined up by chance from our viewpoint? Motion helps answer that. By measuring redshift and blueshift, the stretching or compression of light due to motion, scientists estimate velocities along our line of sight. If two galaxies are near each other in space and share compatible motions, an interaction becomes much more plausible. Spectroscopy also reveals gas turbulence, inflows, outflows, chemical composition, and stellar ages. A galaxy's light can be split into fingerprints. Those fingerprints are wonderfully talkative. Consider star formation. If astronomers see many hot young stars, bright hydrogen emission regions, and infrared dust heating concentrated where tidal features intersect, they infer merger-triggered starbursts. If they detect two active galactic nuclei in one disturbed system, they infer two central black holes not yet fully merged. One famous example is NGC 6240, where observations reveal two supermassive black holes in a chaotic merger remnant. That is the sort of sentence astronomy gets to write with a straight face. Two black holes, same galaxy, mid-merger. Astronomers also use statistics. By surveying many galaxies at different distances, they look back in time because light takes time to travel. A galaxy 1 billion light-years away is seen roughly 1 billion years in the past. More distant galaxies reveal earlier cosmic eras. This allows scientists to ask, were mergers more common long ago? Evidence suggests yes. In the younger universe, galaxies were closer together, richer in gas, and interactions more frequent. Mergers likely played a major role in building today's large galaxies. So observing distance becomes observing history. Every deep image is partly an archive. Citizen science has even joined the effort. Projects like Galaxy Zoo invited the public to classify galaxy shapes and identify mergers in huge imaging surveys. Human pattern recognition proved useful in spotting tidal tails, warped disks, and odd structures. Millions of people helping sort galaxies is a quietly charming sentence. The cosmos can be communal. Then there are computer simulations. These are not separate from observation. They are partners to it. Astronomers build models containing stars, gas, dark matter, and gravity, then let systems evolve under physical laws. By adjusting masses, angles, speeds, and gas content, they compare outcomes with real observed galaxies. If a simulation reproduces a specific tidal tail, bridge, or double-core structure, it can suggest what path the galaxies likely took. A strange photograph becomes reconstructable motion. The famous Toomey brothers pioneered some of this work in the 1970s using comparatively simple models that beautifully demonstrated how tidal tails emerge from gravitational encounters. Since then, simulations have become vastly more sophisticated, including hydrodynamics, star formation, feedback, magnetic fields, and dark matter structure. Computers let astronomers watch what time denies. How do scientists estimate where a merger is in its timeline? They examine separation of the cores, shape of tails, starburst ages, gas distribution, and orbital modelling. A widely separated pair with mild distortion may be early stage. A chaotic system with two close nuclei may be later stage. A smooth elliptical with faint shells may be post-merger. No universal clock exists, but clues accumulate. Astronomy often works like detective work with excellent photographs. What about our own future? Researchers model the coming encounter between the Milky Way and the Andromeda Galaxy using measured masses, velocities, and uncertainties. Simulations explore whether the first pass happens sooner or later, how the Triangulum Galaxy might participate, and what final remnant could emerge. So astronomers are already studying a collision that has not yet occurred. Science enjoys arriving early. There are limitations, of course. Distances can be uncertain. Dark matter distributions are inferred, not directly seen. Three-dimensional motions are harder to measure than sky positions alone. Star formation physics is complex. Dust hides things. Yet even with these challenges, the broad picture is robust. Galaxies interact, merge, trigger starbursts, grow black holes, and change shape. The evidence comes from many independent lines. That convergence is powerful. There is something beautiful about how humans study such slow events. We cannot wait billions of years. So we compare many systems, decode light, simulate gravity, and let distant galaxies teach us through variety. Patience replaced by inference, time replaced by method. Are galaxy collisions exceptional spectacles, or one of the main ways the universe builds itself? It is tempting to hear the word collision and think only of damage. On Earth, collisions often mean broken glass, dented metal, spilled groceries, and the sudden need to explain yourself. Our daily experience teaches that impact destroys order. So when we imagine galaxies colliding, we instinctively picture cosmic wreckage. But the universe has a broader definition. In astronomy, collisions are often an act of construction. Galactic mergers do tear apart older structures. Spiral arms can be stretched beyond recognition. Gas clouds are shocked. Stellar orbits are rewritten. Distinct identities blend into one remnant. Yet from these disruptions come larger galaxies, new stars, richer chemistry, growing black holes, and the hierarchical architecture of the cosmos we observe today. Without collisions, the universe would look very different. Perhaps smaller, perhaps simpler, certainly less assembled. Let us begin with the early universe. After the Big Bang, matter was not distributed as finished galaxies waiting politely to be photographed. It was a growing web of gas and dark matter with slight density differences. Over time, gravity amplified those differences. Denser regions attracted more matter. Dark matter halos formed. Gas fell inward. The first stars and primitive galaxies emerged. These early galaxies were generally smaller than many large galaxies we see today. How did the giants form? Partly by merging, small systems combined into larger ones. Those larger ones later combined again. This step-by-step growth is called hierarchical structure formation. It is one of the central ideas in modern cosmology. The universe did not build everything at once. It stacked complexity gradually. Imagine villages becoming towns, towns becoming cities, cities becoming sprawling metropolitan regions, but with stars, gas, and several billion years of scheduling flexibility. Every large galaxy likely carries evidence of this layered history. Our own Milky Way appears to have grown through both internal evolution and the accretion of smaller galaxies. Stellar streams in the halo reveal remnants of past mergers. Different star populations preserve chemical and orbital clues to ancient companions now absorbed. Home, in part, is inherited matter. That is a surprisingly intimate fact. Galactic collisions also help build stars. When gas-rich galaxies interact, tidal forces compress clouds, drive gas inward, and trigger starbursts. Regions once quiet can suddenly form stars at elevated rates. Massive clusters appear. New stellar generations light up the remnant. So while old structures are dismantled, fresh suns are born. A merger can therefore increase the total stellar population and change the future of planetary formation. Some of the stars that shine today in merged galaxies likely owe their existence to collisions long ago. That includes potential future planetary systems, and perhaps life. Chemistry deepens too. Massive stars formed during merger-triggered starbursts lie fast and die young as supernovae. Those explosions forge and disperse heavy elements: oxygen, carbon, iron, silicon, calcium, and more. Later generations of stars and planets inherit that enriched material. Rocky worlds need previous stars. Complex biology likely benefits from chemical richness. Collisions can accelerate the recycling process. So even something as ordinary as a stone beneath your feet depends on ancient cosmic events that were not especially gentle. There is also the matter of black holes. Most large galaxies host central supermassive black holes. During mergers, gas can be funneled toward galactic centers, feeding these black holes and helping them grow. When galaxies with central black holes merge, the black holes themselves may eventually combine. Thus collisions help build some of the most massive black holes in the universe. A giant black hole may be less an isolated monster and more an archive of repeated growth episodes, meals, mergers, patience. The visible shapes of galaxies are also sculpted by collisions. Many giant elliptical galaxies likely form through major mergers of spirals and subsequent accretion of smaller companions. Their smooth, rounded appearance can be the final settled form of long dynamical histories. In that sense, collisions diversify the universe. Without them, spiral disks might dominate more completely. With them, we get spirals, ellipticals, lenticulars, shells, streams, giant cluster centrals, and a rich zoo of structures. The sky becomes more interesting through interaction. This is true beyond galaxies too. Planetary systems gain complexity through impacts and accretion. Continents form through collisions of plates. Even biological innovation sometimes follows environmental disruption. Nature often uses disturbance as a creative tool. Now let us consider clusters of galaxies. In rich clusters, hundreds or thousands of galaxies inhabit shared gravitational wells. Over time, mergers and interactions help central galaxies become enormous. Gas between galaxies is heated. Dark matter halos combine. The cluster itself grows hierarchically, much as galaxies do, so the principle scales upward. Small halos merge into larger halos. Galaxies merge into larger galaxies. Groups merge into clusters. The universe builds like nested systems of gathering. This hierarchical growth is strongly supported by observations and simulations. Large ski surveys map galaxy populations across cosmic time. Distant galaxies, seen earlier in the universe's history, often look smaller, clumpier, and more interaction-rich than many nearby mature systems. The farther we look, the younger structure appears. The younger structure appears busier. That is exactly what the model predicts. Computer simulations using dark matter and gas physics reproduce filamentary cosmic webs, halo mergers, galaxy growth, and many statistical properties of the observed universe. Collisions are not side stories. They are part of the main engine. What if collisions never happened? Galaxies might remain more isolated and smaller on average. Star formation histories would differ. Giant ellipticals might be rare or absent. Supermassive black holes could grow more slowly. Chemical enrichment patterns would shift. The universe might still be beautiful, but it would not be the same universe we know. Less blended, less layered, perhaps less surprising. There is a philosophical comfort here. We often imagine stability as ideal and disruption as failure. Yet cosmic history suggests some forms of order require repeated restructuring. Systems grow by absorbing, adapting, and recombining. The Milky Way itself is not a pristine, untouched object preserving one ancient blueprint. It is a living composite shaped by billions of years of interactions. Even our future encounter with the Andromeda Galaxy is part of that same process. We are not witnessing an exception in advance, we are witnessing continuity. Another useful reminder: collision in astronomy usually means long gravitational merging, not instantaneous smashing. Because stars are far apart, much of the action is orbital and structural. Matter is reorganized more than pulverized. That nuance matters. The universe often creates by rearranging existing ingredients rather than inventing from nothing. There are echoes of that everywhere. Cities rebuild from old materials. Languages borrow and merge. Ideas combine into better ideas. Galaxies grow from previous galaxies. Even the atoms in your body were assembled from older stars and recycled through multiple generations of cosmic change. You are merger-era matter with opinions. One of the most elegant consequences of collisions is that they make time visible. Tidal tails, shells, streams, and distorted cores are historical signatures. A galaxy can carry marks of ancient encounters for billions of years. The universe remembers construction through scars. That is not a bleak thought. It is a generous one. Evidence of change survives long enough for latecomers like us to learn from it. As galaxies continue evolving, collisions may become less frequent in some regions, as expansion separates distant systems more strongly. Local groups and clusters still interact, but the far future universe may isolate many structures from one another. We happen to live during an era when much of the building is still legible. That is fortunate timing. Imagine stepping outside at night and discovering that patience had been removed from the universe. The stars are still there, the dark is still there, but time itself has accelerated enough that motions normally hidden across millions of years now unfold in front of your eyes like weather. That is tonight's thought experiment. If time were fast enough to watch a galactic collision directly, what would you see? We live in a slow-motion cosmos. Nearly everything grand happens too gradually for human senses. Mountains rise too slowly to notice. Continents drift too slowly to hear. Stars evolve too slowly to mourn in real time. Galaxies merge so slowly that whole civilizations could rise, vanish, and be forgotten during a single early stage. Because of that slowness, the night sky feels fixed. It is not fixed. It is simply courteous enough to move gently. Now imagine that courtesy withdrawn. Suppose millions of years pass each second while you remain a calm observer, safely outside the system, watching two large spiral galaxies approach one another. At first, they seem suspended in darkness, two glowing islands of stars separated by black space. Each rotates gracefully. Spiral arms turn around bright central bulges. Dust lanes drift like dark seams across luminous disks. Then, almost immediately by your new standards, they begin to move, not rushing wildly, sweeping, curving inward through mutual gravity. You would notice something surprising first. They do not head straight into one another like thrown stones. They arc. They bend around a shared centre of mass. Their paths loop and adjust. Gravity prefers curves to collisions. As the galaxies draw nearer, the outer arms begin to distort. One arm stretches longer than before, another twists backward. The clean symmetry of each spiral starts to loosen. This is the first visible sign that identity is temporary. Then comes the close pass. The two disks slide near each other, partially overlapping in perspective. Their central regions swing past rather than immediately merging. Long tidal tails erupt outward, vast streams of stars flung into space in opposite directions. If you could watch it in accelerated time, these tails would unspool like ribbons cast by dancers turning too quickly. They would lengthen, curve, and fade into the dark. Some would arc elegantly, others would fork or twist. The galaxies themselves would continue onward for a while, pulled apart again after the first encounter. That might confuse first-time viewers. Was that it? No. Galactic collisions often happen in installments. The galaxies separate somewhat, still distorted, then slow and curve back toward one another. You would watch them loop around and return for another pass. This is where the term dance becomes unavoidable, though galaxies never asked for choreography. During the intervals between close passes, internal changes become obvious. Gas clouds collide and compress. Bright knots of star formation ignite across the disks and bridges between them. New clusters appear like sudden lanterns in the spiral arms. The galaxies would flicker with episodes of creation. Regions once dim would brighten. Blue-white young stars would briefly dominate local zones. Elsewhere, dust would thicken and obscure portions of the light. The whole scene would feel alive in a biological sense, though it is not biology at all. It is gravity plus time. If your accelerated vision included wavelengths beyond human sight, the show would become even richer. Infrared would reveal warm dust blazing where visible light seems blocked. X-rays would flash from shocked gas and energetic central regions. Radio maps would show vast hydrogen streams stretching farther than starlight suggests. The visible spectacle is only the polite public version. The private version is even busier. Now watch the centres. Each galaxy likely hosts a supermassive black hole hidden in its core. You would not see the black holes themselves unless gas around them glowed, but you might witness central regions becoming intensely bright as matter falls inward. Twin active nuclei could blaze inside the merging structure like two furnaces moving toward eventual union. Jets might appear, winds might erupt. The calm centres of former spirals would become places of concentrated violence. Meanwhile, the stars themselves mostly do not crash. This remains one of the strangest truths. Despite the dramatic appearance, individual stars pass through the merger with enormous empty distances between them. They alter orbits, yes. They are flung outward, pulled inward, scattered into new trajectories, but direct star-on-star impacts are rare. So if you watch closely enough, the galaxies would behave more like ghostly swarms interpenetrating than like solid objects smashing. This is a useful lesson in scale. What looks dense from afar is mostly emptiness up close. There may be wisdom there beyond astronomy. As repeated passes continue, the spiral arms become less distinct. The once flat disks thicken. Ordered rotation gives way to broader, more randomized stellar motion. The galaxies stop looking like two elegant pinwheels and start resembling one chaotic, luminous storm. Then slowly, even that storm begins to settle. The central cores sink together. The two black holes spiral inward over long-hidden timescales. Outer tidal tails continue drifting, some falling back, some dispersing into halos. Starburst regions fade as fuel is consumed. The merger remnant rounds out. The final system often resembles a giant elliptical galaxy, broader, smoother, less sharply patterned. If spirals are sentences, ellipticals are summaries. You would have watched two articulate structures become one quieter statement. There is something emotionally strange about accelerated time. Beauty appears, peaks, and dissolves almost immediately. Tidal tails blossom and fade. Bright starbursts ignite and disappear. Structures requiring eons to form would last moments in your perception. You might begin to understand that permanence is partly a matter of viewing speed. Even our own lives feel solid because we inhabit them at human tempo. Speed things up enough, and cities become sparks. Slow them down enough, and clouds become sculpture. Now imagine watching the future meeting of the Milky Way and the Andromeda Galaxy this way. Two familiar spirals turning quietly, then approach, distortion. Long stellar rivers cast into darkness, repeated sweeping passes, a final blended remnant often nicknamed Milkomeda, home transformed before your eyes. The thought carries a subtle tenderness. We often think the universe changes elsewhere, yet our own galaxy is part of the same process, only scheduled later. Would such a time-lapse feel violent or graceful? Both. There would be no explosions in the cinematic sense dominating every moment. Instead, there would be continuous restructuring, streams, arcs, brightening knots, fading lanes, shifting centres, endless orbital revision. Violence in astronomy is often elegant from a distance. Grace can be built from force. What would you feel after watching many such mergers? Perhaps humility, perhaps comfort, perhaps suspicion that stillness is never as complete as it seems. Because once you have seen galaxies move quickly, you can never again mistake the night sky for something frozen. You would know every star field is mid-process, every shape is temporary, every calm arrangement is a phase. At last, after the tails have faded, after the bright bursts of newborn stars have dimmed, after the long loops of repeated passes have ended, the galaxies become quiet again. Not silent. The universe is never truly silent in any complete sense. Stars still orbit. Gas still drifts. Black holes still wait. Light still travels across distances so large they humble language. But compared with the turbulent ages of collision, something like calm returns. Two former galaxies have become one new home. This is where our journey ends tonight. We began with the idea of impact, with the dramatic phrase, "when galaxies collide," and perhaps with instincts shaped by life on Earth. Here, collisions often mean endings, broken things, sudden change, loss of shape. But the cosmos offered a different version. Galactic collisions are rarely simple destruction. They are long negotiations of gravity. They are rearrangements more than ruin. They are old structures giving way so new structures can exist. Spiral arms may disappear, yet new stars are born. Distinct centres may merge, yet larger systems emerge. Paths are lost. New paths are written. Again and again, the universe shows that change and damage are not identical ideas. That may be worth carrying back into ordinary life. Imagine the final remnant of a great merger, a giant elliptical galaxy glowing with the accumulated light of trillions of stars. Somewhere in its halo drift faint streams from ancient tidal tales. Somewhere in its centre rests a larger black hole built from older unions. Somewhere in its outer reaches, quiet stars circle with planets no one has named. If life exists there, it may look up and consider its galaxy stable, permanent, complete. It would be mistaken in the same way we often are. Even settled things continue becoming. That is one of the gentlest lessons astronomy offers. Stability is often movement that has found a slower rhythm. Our own Milky Way feels ancient and dependable tonight. The band of stars across the sky seems timeless, yet it is rotating, evolving, consuming small companions, forming stars, losing stars, and gradually approaching the Andromeda Galaxy. The future merger is not a break from normality. It is normality on a larger clock. We humans live by days, seasons, and generations. Galaxies live by hundreds of millions of years. Because their clocks are slower, we call them fixed. But slowness is not permanence. That truth appears everywhere once noticed. Mountains erode, languages drift, cities rebuild themselves street by street, relationships change shape, bodies age. Ideas merge with newer ideas and become something neither original version expected. The universe and ordinary life are not as separate as they seem. Both are full of transformations that feel sudden only when viewed too closely, or invisible when viewed too briefly. There is also comfort in scale. If galaxies can survive collisions and become larger, calmer homes afterward. Perhaps change need not always be feared simply because it arrives with disorder first. The night sky is full of examples of endings that are also beginnings. Stars die and seed future worlds. Clouds collapse and ignite suns. Galaxies merge and create new structures. Even darkness carries light long enough for latecomers to learn from it. We are among those latecomers, tiny beings on a small planet around an ordinary star, able to understand that the faint glow overhead is not decoration but history in motion. That is an extraordinary privilege. Tonight, somewhere beyond naked sight, real galaxies are interacting right now. Tails are stretching, gas is compressing, black holes are spiraling inward, new stars are turning on in dusty knots. Elsewhere, ancient merger remnants drift in smoother forms, their dramatic youth now hidden beneath calm appearances. The cosmos contains both turbulence and rest simultaneously. So do we. If you ever feel that change has made life unrecognizable, remember that the universe builds many of its grandest things by rearranging what came before. Nothing remains exactly the same. That is not always tragedy. Sometimes it is how growth looks from the inside. And if, billions of years from now, some future observer stands beneath the sky of the merged Milky Way and Andromeda, they may see no trace of the neat spirals we know now. They may inherit a broader glow, a different centre, a changed home, yet they will still be under stars, they will still wonder, they will still belong to the same unfolding story. Thank you for spending this quiet stretch of time here with me in Science for Sleep. If this journey soothed your thoughts or gave your mind somewhere gentle to wander, you're always welcome back. Wherever you're listening from tonight, I hope the room is calm, the air is kind, and your thoughts can grow a little quieter now. And as the universe keeps changing at its patient pace above us, you can rest here for a while beneath it.